When you think about planets, your mind likely pictures the familiar worlds of our own solar system, from sun-scorched Mercury and the veiled expanse of Venus, to our blue Earth, the red dust of Mars, the colossal gas giants, Jupiter and Saturn, and the frozen, distant orbs of Uranus and Neptune. Yet far beyond this stellar neighborhood, countless other stars are orbited by billions of their own planets, known as exoplanets. The exploration of these alien worlds represents one of the most captivating frontiers in contemporary astronomy. Just a few decades ago, the very notion of detecting a planet outside our solar system felt like something out of science fiction. Stars are so incredibly luminous and planets so comparatively faint that the prospect of identifying one across such enormous distances seemed almost hopeless. Consider that even our closest stellar neighbor, Proxima Centauri, is 4 light-years away, and any planet orbiting it would be an infinitesimally small point of light, completely engulfed by the star's glare. However, a groundbreaking event in 1995 permanently altered the trajectory of astronomy. It was then that Swiss astronomers Michel Mayor and Didier Queloz revealed their discovery of the first exoplanet circling a star similar to our Sun. This world, designated 51 Pegasi b, was a giant comparable to Jupiter, yet it orbited so close to its star that its surface temperature soared to nearly 1,000 degrees Celsius. This finding was a true sensation, heralding the start of a new era dedicated to hunting for worlds beyond our own. Since that time, the techniques for identifying exoplanets have advanced significantly. Among the most fruitful is the transit method, which involves astronomers monitoring a star for the minuscule reduction in its brightness that occurs when a planet crosses in front of it. This task demands unbelievable precision, as the starlight might dim by just a tiny fraction of 1%. Another key technique is radial velocity measurement, where the mutual gravitational tug between a star and a planet causes the star to wobble slightly, a movement that can be detected through shifts in its light spectrum. As time went on, space telescopes were engineered specifically for the task of finding exoplanets. The Kepler mission transformed the field by identifying thousands of potential candidates, and its successor, the TESS mission, broadened the search to encompass nearly the entire celestial sphere. We have now learned that planets are not an anomaly. Instead, they are the standard. Nearly every star is host to at least one planet, and many possess entire systems of them. What is even more remarkable is the sheer diversity among these exoplanets, which range from gas giants orbiting so near their stars that their atmospheres are boiling away, to rocky planets that could have oceans and atmospheres where life might emerge. When you look up at the night sky now, you can understand that each tiny point of light, every faraway star, might conceal whole new worlds that we are only just starting to uncover. Our search to find a second Earth has truly only just begun. The effort to detect planets beyond our solar system is, at its core, the practice of capturing the most subtle indications of their presence. Exoplanets are so diminutive and dim in comparison to their stars that observing them directly is only achievable in very rare circumstances. Consequently, astronomers have devised clever indirect strategies to find them by observing their effects on a star's light or its motion through space. One of the most effective of these strategies is the transit method. Picture a planet crossing directly between its star and us, thereby blocking a tiny portion of its light. For an observer here on Earth, this event manifests as a small recurring dip in the star's luminosity. Identifying such a dip requires instruments of incredible sensitivity and can demand months or even years of continuous observation. This approach, famously employed by the Kepler telescope, is responsible for the majority of our exoplanet discoveries, though it is only effective for planets with orbits perfectly aligned with our line of sight. Another prevalent technique is the measurement of radial velocity. A planet's gravitational pull makes its host star wobble in a small circular path. This slight motion alters the star's spectrum because of the Doppler effect. As the star moves toward us, its light shifts toward the blue end of the spectrum, and as it recedes, the light shifts toward the red. By carefully measuring these spectral shifts, astronomers can deduce a planet's existence, approximate its mass, and calculate its orbital distance from the star. Even more sophisticated methods have been developed as well. Astrometry involves precisely measuring the tiny shifts in a star's position against the backdrop of the sky, caused by a planet's gravitational influence. Gravitational microlensing leverages Einstein's theory of general relativity. If a planet aligns perfectly in front of a more distant star, its gravity will bend and magnify the background starlight, causing a brief, detectable brightening. Direct imaging, while uncommon, provides breathtaking results by using special masks called coronagraphs to block a star's intense light, revealing the faint specks of orbiting planets. Frequently, astronomers will utilize a combination of methods to verify a new discovery and paint a more complete picture. For instance, observing a planet's transit can reveal its physical size, while radial velocity measurements can determine its mass. By putting these two pieces of data together, scientists can calculate the planet's density, which helps them distinguish between rocky terrestrial worlds, massive gas giants, or other types of planets in between. These technologies are being refined every year. We are now capable of detecting planets the size of our own Earth, and in the decades to come, we may be able to analyze their atmospheres and perhaps even discover direct evidence of life. All of this is possible just by scrutinizing the subtle changes in the light that reaches us from distant stars. In the early days of exoplanet research, scientists largely presumed that other star systems would follow the blueprint of our own, with small rocky planets close to the star and gas giants farther out. The very first discoveries, however, completely upended these expectations. It turned out the universe was far more creative and varied than we had ever conceived. One of the initial major surprises was the discovery of so-called hot Jupiters, which are immense gas giants that orbit their stars at extremely close distances. The planet 51 Pegasi b, for example, completes a full orbit in merely 4 Earth days, leading to temperatures that can climb to between 1,000 and 2,000 degrees Celsius. On such worlds, atmospheres are in a constant state of boiling, sometimes forming vast tails of gas that trail off into space, leaving astronomers to wonder how these massive planets got so close to their stars in the first place. Another fascinating classification of exoplanet to emerge is the super-Earth. These are worlds that are more massive than our own planet, but are considerably smaller than gas giants like Neptune. Their existence points to a common type of planet in the galaxy that, curiously, is entirely absent from our own solar system, adding yet another layer to the complex and surprising tapestry of planetary systems. Exoplanets can be rocky worlds with solid ground and potential oceans, or they might be completely enveloped in dense layers of gas. Some of these bodies, known as super-Earths, are found within their star's habitable zone, a region where conditions might permit liquid water, making them top targets in our quest for extraterrestrial life. We've also discovered mini-Neptunes, a category of planets that fall somewhere between Earth-like worlds and ice giants, which may possess thick atmospheres over layers of ice and possibly even oceans hidden deep beneath the surface. Our own solar system contains nothing like these worlds, which makes them particularly captivating objects of study. Just as compelling are the theoretical ocean planets, imagined as being covered entirely by a single, globe-spanning body of water. Picture a world without any land, where a vast ocean plunges thousands of kilometers deep, eventually meeting a layer of ice compacted by unimaginable pressure above a warm planetary core. If life were to arise there, it would have evolved in a boundless aquatic realm, with no concept of solid ground. Some planets trace wildly elliptical paths, subjecting them to chaotic climate swings between freezing and scorching temperatures. In contrast, other worlds are rogues, untethered to any star and drifting through the frigid emptiness of interstellar space, their only warmth coming from internal radioactive decay and leftover heat from their formation. The sheer diversity of these discoveries has completely reshaped our understanding of how planetary systems come to be, revealing that the laws of physics permit countless configurations beyond the one we call home. When astronomers like me search for life beyond Earth, our first step is to identify planets within the habitable zone, that orbital sweet spot around a star where surface temperatures could support liquid water. The reason for this focus on water is simple. Here on Earth, it serves as the universal solvent and the essential medium for every form of life we know. While other biological chemistries might be possible, you have to begin your search with the one example you understand. The precise location of a star's habitable zone is dictated by its brightness and heat output. For a star like our Sun, this zone stretches roughly from the orbit of Venus to that of Mars. If a planet is too close, like Venus, its water boils away. If it's too far, like Mars, its water turns to ice. However, merely residing in this zone is no guarantee of habitability, as many other factors, including atmospheric composition, pressure, the presence of a magnetic field, and geological activity, play a critical role. Because stars themselves differ, so do their habitable zones. Luminous, hot stars possess broader habitable regions, but have much shorter lifespans, which may not provide enough time for complex life to emerge. Conversely, faint red dwarfs have habitable zones that are much closer in, but planets orbiting there are likely to become tidally locked, with one side perpetually baked by the star's heat and the other frozen in darkness. Such a world could still be habitable, as an atmosphere or oceans might redistribute heat, creating a temperate band between the day and night sides. Recognizing these complexities, scientists now embrace the idea of a broad habitable zone, acknowledging that life could thrive under conditions we once considered impossible. For instance, Europa and Enceladus, which are moons orbiting Jupiter and Saturn respectively, conceal vast liquid oceans beneath their icy shells, kept warm by the constant squeezing and stretching of tidal forces. This discovery implies that even planets well outside the conventional habitable zone might harbor life in subsurface environments. To truly evaluate a planet's potential for life, astronomers employ sophisticated models that account for everything from atmospheric chemistry and pressure to the effects of greenhouse gases, planetary rotation, and axial tilt. It turns out that minor variations in these parameters can be the difference between a lush paradise and a world that is completely inhospitable. Ultimately, the search for planets in the habitable zone is not just about finding a potential second Earth. It's a profound investigation into how unique our own world truly is in the vastness of space. While we don't yet have the technology to directly view the surfaces of these distant worlds, we can analyze their atmospheres in great detail. Even from tens or hundreds of light years away, A planet's atmosphere acts as its unique fingerprint, carrying encoded information about its chemical makeup, temperature, climate, and even the potential presence of life. The main technique used for this is called transit spectroscopy, which involves observing a planet as it passes in front of its parent star from our point of view. As the planet transits, a tiny fraction of the starlight shines through its atmosphere, and different gases within that atmosphere absorb light at very specific wavelengths. This process leaves distinctive dark lines or gaps in the star's spectrum. By carefully analyzing these gaps, scientists can identify the chemical components present, such as water vapor, methane, carbon dioxide, ammonia, or oxygen. Finding water vapor, for example, hints at the existence of oceans or clouds, while detecting methane and oxygen together could be a powerful biosignature, a tantalizing clue pointing to biological processes at work. Another method for studying these atmospheres occurs during a planetary eclipse, when the planet disappears behind its star. By comparing the star's light spectrum just before and after the planet is hidden, astronomers can isolate the planet's own thermal emissions. This data can reveal crucial information about the planet's temperature and whether its atmosphere contains clouds or dust. The variety we've observed is staggering. Some hot Jupiters have atmospheres so intensely heated that they contain vaporized metals, while certain super-Earths may suffer from runaway greenhouse effects that make them utterly uninhabitable. Modern instruments, most notably the James Webb Space Telescope, are already providing us with incredibly detailed studies of exoplanet atmospheres. The initial findings have been nothing short of astonishing, revealing worlds with clouds made of crystals, rain composed of molten iron, and signs of complex chemical reactions occurring deep within the atmospheres of gas giants. Each new analysis brings us a step closer to answering the ultimate question of whether we are alone. And perhaps, buried in the spectral data from a distant world, we will one day find the clear, subtle sign of another living world. Over the last few decades, we have cataloged thousands of exoplanets, many of which are so strange that if you saw them in a science fiction movie, you would likely dismiss them as pure fantasy. But these worlds are real, their existence confirmed through careful observation. A famous example is the gas giant HD 189733b, which orbits its star in just 2 Earth days. On this world, winds howl at speeds exceeding 8,000 kilometers per hour, and the atmosphere is filled with silicate particles, meaning it experiences sideways rain made of molten glass. Then there is Kepler 16b, a planet that orbits not 1 but 2 suns. If you could somehow stand on its surface, which is probably a swirling gas, you would witness a double sunset on the horizon, a sight remarkably similar to the iconic twin suns of Tatooine from Star Wars. These discoveries constantly remind us that the universe is far more imaginative and varied than we ever thought possible, and that our solar system is just one of many countless possibilities scattered across the cosmos. Merely a few decades ago, the idea that planets existed outside our solar system was purely theoretical. Scientists held a strong suspicion of their presence, reasoning that since stars coalesce from clouds of gas and dust, the surrounding disks should naturally form planetary bodies. Yet, up until the 1990s, we lacked a single piece of confirmed evidence. That all changed in 1992 with a stunning announcement from astronomers Alexander Volsjan and Dale Frail. They had discovered planets orbiting the pulsar PSRB 1257 plus 12. A pulsar is a type of neutron star, the dense remnant of a supernova, which emits beams of radio waves with incredible regularity. The astronomers noticed tiny variations in these pulses, leading them to the precise conclusion that the dead star was accompanied by small planetary companions. This finding was shocking for a couple of major reasons. Firstly, it was widely believed that no planet could possibly endure the monstrously high radiation levels in the vicinity of a pulsar. Secondly, these were the very first exoplanets ever confirmed. Yet they were profoundly inhospitable worlds. Dark, intensely irradiated, and adrift in the cosmic void. The genuine revolution in this field, however, arrived in 1995. It was then that Michel Mayor and Didier Queloz of the University of Geneva revealed their discovery of 51 Pegasi b, a gas giant orbiting a star much like our own Sun. This marked the first instance of a planet found around a main sequence star, and introduced us to the first hot Jupiter. The technique they employed, known as radial velocity measurement, would go on to become a cornerstone in the search for exoplanets. For their work on 51 Pegasi b, its discoverers were awarded the Nobel Prize, an achievement that ignited a passion for exoplanet hunting in dozens of astronomy teams across the globe. That moment truly heralded a new astronomical age. Within just a couple of decades, we progressed from knowing of 0 confirmed planets to cataloging thousands of different worlds, ranging from rocky super-Earths to bizarre gas giants. What I find most remarkable is that a great number of these discoveries have been facilitated by telescopes, both on the ground and in orbit, that can detect fluctuations in starlight as small as 0.001%. Each new exoplanet represents more than a simple addition to a list. It tells a unique story about the universe's incredible diversity, and serves as a poignant reminder that our Earth is but one of innumerable worlds floating in the vastness of space. Without these highly specialized space telescopes, our knowledge of exoplanets today would be limited to a mere fraction of what we have found. These instruments are what elevated the search for other worlds into a methodical, statistically robust science. The true trailblazer in this endeavor was the Kepler Space Telescope, which the National Aeronautics and Space Administration, or NASA, launched in 2009. Kepler's mission was conceptually straightforward, but technically demanding: to stare unblinkingly at one specific patch of the cosmos, chronicling the most minuscule dimming of starlight caused by a planet passing in front of its star. This observatory monitored approximately 150,000 stars at once, with a sensitivity capable of registering brightness changes of less than 0.1%. In only a few short years of operation, Kepler identified thousands of potential exoplanets, a list that included numerous super-Earths, mini-Neptunes, and planets situated within their star's habitable zone. It was through this mission that we gathered our first meaningful statistics, suggesting that about half of all stars might harbor a planet similar in size to Earth or slightly larger, implying the existence of tens of billions of potentially life-sustaining worlds in our galaxy alone. Of course, Kepler was not without its drawbacks. It could only survey a very small segment of the sky, and after a critical failure of its stabilization system in 2013, the mission required a complete overhaul. Renamed K2, it continued its work by observing different celestial regions, though with somewhat diminished accuracy. In 2018, a new planet hunter took over, the Transiting Exoplanet Survey Satellite, more commonly known as TESS. Its objective was to survey nearly the entire sky, concentrating on the brightest and closest stars to us. This strategy differs from Kepler's, as TESS specifically seeks out planets orbiting nearby stars, making them ideal candidates for detailed follow-up studies by other powerful instruments, including the James Webb Space Telescope, or JWST, whose launch in late 2021 marked a monumental leap forward in astronomy. To date, TESS has found hundreds of confirmed exoplanets and thousands more candidates, with its discoveries frequently becoming top priority targets for spectroscopic analysis to probe their atmospheres and determine their composition. Together, Kepler and TESS have demonstrated that planets are not a cosmic rarity, but a fundamental rule of the universe. It's entirely possible that hidden within their data is a world where someone is gazing at their night sky, asking the very same questions we do. Consider the remarkable case of WASP-12b, often called a black planet, which has an atmosphere that captures nearly all incoming light, rendering it one of the darkest celestial bodies known. It orbits so close to its star that its parent body is actively siphoning off material from its surface, ensuring the planet's gradual demise. Scientists predict that in just a few million years, nothing but its core will be left. Another world, Kepler 438b, is a super-Earth within its star's habitable zone and possesses a thick atmosphere, appearing very Earth-like at first. However, its star unleashes frequent and powerful flares that would likely sterilize the planet's surface, reminding us that a world's resemblance to Earth does not guarantee its hospitality to life. Perhaps the most bizarre of all is 55 Cancri e, a rocky planet orbiting so near its star that its surface temperature soars to 2,400 degrees Celsius. A significant portion of its mass is carbon, which, under such extreme conditions, could crystallize into graphite and diamond. It's conceivable that entire continents made of diamond lie just beneath its scorched surface. Every new planet we uncover broadens our perspective on what kinds of worlds are possible, revealing a cosmos far more varied and imaginative than we could have ever conceived. And somewhere within this gallery of cosmic wonders, a planet where intelligent life has emerged might already exist. We just haven't located it yet. While the news of another exoplanet discovery might seem almost mundane today, each one is a completely unique world, a powerful testament to the limitless creativity of our universe. This telescope was engineered not just for observing distant galaxies and nebulae, but also for investigating exoplanets with unprecedented clarity. Its principal instrument is infrared spectroscopy, a technology that enables it to probe the atmospheres of faraway worlds, identify the chemical signatures of specific molecules, and map out the temperature profiles of these planets. Consequently, whenever a planet crosses in front of its star or slips behind it, the James Webb Space Telescope can deconstruct the light, revealing the atmospheric composition with extraordinary accuracy. During its initial months of service, the telescope has already identified evidence of water vapor, carbon dioxide, and hydrogen sulfide within the atmospheres of various exoplanets. This progress brings us to the brink of being able to reliably hunt for biosignatures, molecules like oxygen, ozone, and methane, in particular ratios that are, on our own planet, linked to life. The JWST is currently analyzing the most compelling targets discovered by its predecessors, Kepler and TESS, and in doing so, is assembling the first comprehensive portraits of these alien worlds. For instance, its analysis of the atmosphere of WASP-39b uncovered a complex chemistry, including signs of photochemical reactions that have never been observed outside of our solar system. The future of our search for extraterrestrial life hinges on a new generation of projects. The European Space Agency, or ESA, is developing PLATO, a telescope designed specifically to find Earth-like planets orbiting stars similar to our Sun. In parallel, NASA is conceptualizing the LUVOIR project, a massive observatory that could take direct photographs of exoplanets by using either a specialized coronagraph to block starlight or a separate free-flying shield known as starshade. These advanced missions will empower us to see planets as distinct specks of light, allowing for direct study rather than relying on the indirect method of observing transits. Another significant strategy involves monitoring planets throughout their entire orbits. This long-term observation would enable us to spot seasonal variations and potentially even detect shifts in the surface color of a planet, which could suggest the presence of vegetation or other biological phenomena. All of this research signifies that within the coming decades, you and I might finally get an answer to one of humanity's most ancient questions. Are we alone in the cosmos? And it's possible that this answer will reveal itself not in a grand discovery, but as a subtle line on a spectrogram captured by a telescope, drifting silently in the cold expanse of space as we sleep. Every planet you can see, whether in our solar system or orbiting a distant star, began as part of an immense, rotating cloud of gas and dust. Scientists refer to this method of planetary system formation as accretion. The entire process is initiated by the collapse of a gigantic molecular cloud, which gives birth to a star. A protoplanetary disk then forms around this newborn star, creating a flat structure packed with gas, dust, ice particles, and mineral grains. Within this disk, a slow yet unyielding process of particle accumulation begins. Initially, tiny particles collide and fuse, growing into bodies measured in millimeters, then centimeters, and eventually meters. As they grow, gravity asserts its dominance, leading to the formation of planetesimals, objects that are tens of kilometers across. The collisions between these planetesimals become increasingly energetic, and out of this chaotic dance, the precursors to full-fledged planets gradually take shape. The disk's inner regions, being closer to the star, are significantly hotter, which is why rocky planets such as Mercury, Venus, Earth, and Mars form there. Farther out, beyond what is known as the snow line, temperatures are cold enough for ice to remain solid. This is the domain of gas giants and icy planets, where the abundance of ice boosts the mass of planetary embryos, enabling them to gravitationally capture enormous quantities of gas. This formation process, however, is not always orderly. Sometimes giant planets migrate inward toward their star, violently ejecting other planets from the system, or even consuming them. A scenario that might explain the existence of hot Jupiters. Protoplanetary disks serve as the cosmic laboratories where new worlds are forged, and advanced telescopes like ALMA now permit us to view them in stunning detail. These images show distinct rings and gaps within the disks, which are likely the telltale signs of new planets clearing paths as they form. It's fascinating that some stars host numerous planets in stable, orderly orbits, while others possess very few. The reasons behind this are still being investigated, but are thought to involve the initial mass of the disk, the star's activity, the influence of nearby stars, or even gravitational disturbances from a passing star system. By working to understand how planetary systems come into being, we are moving closer to figuring out just how typical our own solar system really is. It's possible we are a cosmic rarity, possessing a unique combination of stability and conditions favorable to life. Alternatively, there could be millions of systems just like ours, each with its own unique history. While our solar system features 8 planets in relatively stable, almost circular orbits, some other stellar systems are scenes of genuine dynamic chaos, where planets are packed so closely that their gravitational forces create intricate orbital resonances, and a year on one can last just a few Earth days. One of the most remarkable examples of this is the TRAPPIST-1 system, which contains 7 rocky planets orbiting a small red star. Their orbits are interlocked in a chain resonance, meaning the movement of each planet is directly tied to its neighbors. As one planet completes a specific number of orbits, another finishes a synchronized amount, creating a celestial dance that keeps the system remarkably stable, despite how close the planets are to one another. Configurations like this provide scientists with a powerful tool for studying the masses and densities of planets. When 2 planets are in resonance, their gravitational attraction causes them to gently tug on each other, producing slight variations in the timing of their transits. These subtle oscillations allow us to calculate the mass of each planet with high precision. In other cases, multi-planet systems can display even more extreme conditions. In the Kepler 36 system, for example, a rocky super-Earth and a gaseous mini-Neptune orbit so close that they approach each other at a distance of just 1.9 million kilometers, about 5 times closer than the distance between the Earth and our Moon. The sheer difference in the size and makeup of planets can be breathtaking, particularly when you consider how close they are to one another. You also encounter enormous systems that contain more planets than we have. For instance, the star HD 10180 possesses at least 6 planets, with some models indicating there could be as many as 9, making it a close parallel to our own solar system, only with its worlds arranged in a much more compact fashion. Such discoveries carry immense weight because they demonstrate just how varied planetary systems can be. There is no single template for how they should form. The universe seems to utilize every possible combination of mass, distance, and orbital layout, proving that nature's creativity in building worlds is nearly limitless. Through future studies of these multi-planet systems, we might finally grasp what allows some to endure for billions of years, while others are fated to undergo catastrophic upheavals. It's even conceivable that we'll find systems where several planets occupy the habitable zone simultaneously, suggesting that life could potentially evolve on more than one world around the same star. When you picture a planet, you almost certainly envision it orbiting a star, like the Sun, giving warmth to the Earth, or an alien star illuminating some far-off world. Yet space also holds a different kind of planet, one that has no star to call its own. These are known as rogue planets, or free-floating planets, objects that wander through total darkness, lit only by the faint glow of distant stars and their own minimal internal heat. Scientists speculate that our galaxy could harbor more of these starless worlds than it does actual stars. They might originate in conventional planetary systems, only to be thrown out later by gravitational disturbances. For example, if 2 giant planets pass too close, one could violently eject its smaller neighbor into the void of interstellar space. Alternatively, a star passing nearby could disrupt the orbits of an entire system, sending its planets on a journey as eternal wanderers. It's also possible some rogue planets formed in isolation, much like tiny stars. but simply didn't have enough mass to ignite the thermonuclear reactions at their core, placing them somewhere between gas giants and brown dwarfs. Life on such a planet seems unimaginable, given the absence of heat and light from a star. However, the scientific hypotheses are genuinely surprising. If a planet has a thick hydrogen atmosphere, it could trap its own internal heat for billions of years. Beneath a thick crust of ice, an ocean could be kept liquid by warmth from the radioactive decay of rock, or by the tidal forces exerted by a large moon, creating a potential haven for life in perpetual darkness. Finding these objects is exceptionally challenging because they don't pass in front of stars to create transits or cause the telltale orbital wobble in a host star. The primary detection methods rely on gravitational microlensing, which occurs when a planet's gravity bends the light of a distant star behind it, and on infrared telescopes that can spot their faint thermal signatures. Every rogue planet that we manage to identify serves as a powerful reminder that the universe is teeming with unexpected forms of existence. These discoveries show us that worlds are not always bound to a sun. They can be cosmic outcasts and still potentially conceal vast oceans, and, perhaps, the secret to life evolving under the most extreme conditions you can imagine. The cosmos has a clear preference for extremes, and planets are certainly no exception to this rule. Among the thousands of exoplanets now known to us, you'll find everything from frozen worlds with temperatures approaching absolute zero, to blistering giants where metals boil and turn into atmospheric clouds. These extreme examples help scientists define the very limits of planetary existence. Let's begin with the super-cold planets. These worlds are either located at immense distances from their stars, or, like rogue planets, have no star whatsoever. Their surface temperatures can plummet to 200 Kelvin or even lower. A perfect example is the planet OGLE 2016 BLG 1195LB, which, though similar in mass to Earth, orbits a faint red dwarf so far away that it is likely trapped in an everlasting frozen night, where any atmosphere would be frozen solid. At the opposite end of the spectrum, you find the ultra-hot planets, such as WASP-12b or KELT-9b, which orbit so perilously close to their stars that their atmospheres reach temperatures exceeding 2,500 to 3,000 Kelvin. KELT-9b circles a star hotter than most, and the intense radiation tears molecules in its atmosphere apart into individual atoms, allowing metals like titanium and iron to vaporize and form clouds. There are also worlds known as ultra-hot super-Earths, which are rocky planets with surfaces that are quite literally oceans of molten lava. Take the planet 55 Cancri E, where the temperature climbs to 2,000 Kelvin. Its dayside might be a vast magma ocean, while at night a thin crust may form, only to be melted once again with each new dawn. These extreme worlds offer astronomers remarkable opportunities for study. The hot planets function as natural laboratories for observing chemistry under conditions similar to those inside stars, while the cold worlds help us model how atmospheres and water might survive with almost no external heat. They also serve as a stark reminder that, by cosmic standards, Earth is an exceptionally comfortable and rare haven where the temperature allows liquid water to exist and life to flourish. When you consider the movement of planets, your mind likely defaults to an orderly arrangement like our solar system, where every planet orbits in the same direction along nearly perfect circles. However, the universe seldom adheres to such neat and tidy patterns. Among the exoplanets discovered, we have found worlds with bizarre orbits that are highly elongated, steeply inclined, or even retrograde, meaning the planet orbits in the opposite direction of its star's spin. Let's start with those elongated orbits. These paths are more like stretched-out ellipses, causing a planet to swing incredibly close to its star at one point and then move very far away at another. A dramatic example is the exoplanet HD 80606b, which endures a wild temperature fluctuation from about 500 Kelvin to nearly 1500 Kelvin as its orbit brings it scorching hot close to its parent star. This kind of extreme heating and cooling cycle can generate incredible atmospheric storms, driving ferocious winds that are capable of circling an entire planet in a matter of hours. Another form of orbital anomaly involves planets with highly inclined orbits, where they circle their star at angles of tens of degrees relative to its equator. These tilted paths are often the result of gravitational interference from other planets or companion stars, which can disrupt a planet's climate, radically alter its seasons, or even shift its axis of rotation. The most perplexing arrangements are retrograde orbits, in which a planet travels in the opposite direction of its star's spin. While this may seem physically impossible, astronomers have already confirmed the existence of such worlds, including the exoplanet WASP-17b. The prevailing theory is that their orbits were violently reversed by catastrophic events, like a near miss with another massive planet or a passing star, giving scientists a clear sign of a turbulent past. Whenever we identify a retrograde or steeply inclined orbit, it serves as a powerful clue that the system has endured tremendous turmoil. You can imagine gravitational battles where some planets were flung into deep space, while others were forced onto these bizarre trajectories. The study of these systems is also critical in the search for life, as a planet on a highly elongated orbit might repeatedly exit the habitable zone, preventing a stable biosphere from developing. At the same time, these worlds reveal just how flexible and creative nature can be, suggesting life might find a way to adapt to even the most chaotic cosmic dances. When you hear the word planet, your mind likely pictures a world similar to Earth, with rock, water, and an atmosphere. Yet, deep space holds worlds with such extraordinary chemical makeups that they feel like they belong in science fiction. Among the most stunning are the diamond planets, where you can envision a world whose structure is largely composed of pure, crystallized carbon. Such a planet could form in a carbon-rich nebula, where immense internal pressures and temperatures would favor the creation of diamonds. The exoplanet 55 Cancri E is a leading candidate for such a world, with scientists theorizing it has a mantle rich in diamond and graphite, all hidden beneath a blistering ocean of lava. Beyond that, you have metallic planets, which might possess an iron core that constitutes nearly their entire mass, leaving little to no room for a rocky crust. Equally mind-boggling are the true snowball planets, which are far more extreme than our own ice giants like Uranus and Neptune. These worlds are made almost entirely of water ice or solid methane, with temperatures so low that their very atmospheres can freeze and crystallize onto the surface, forming layers that are kilometers thick. There are even more speculative hypotheses, including planets made of pure quartz, or those loaded with rare minerals that we find only in trace amounts here on Earth. If such a body formed in the vicinity of a supernova, or within a region of unusual chemical abundance, its interior could be a literal treasure trove of what we consider precious elements. These potential worlds highlight the incredible diversity of the cosmos. While our solar system features only a few fundamental types of planets, the galaxy may contain hundreds of different varieties. For astronomers, this diversity is more than just a novelty, as a planet's chemical composition dictates its climate, density, geology, and its word to hold an atmosphere. It also means that one day, we might discover a world where it literally rains diamonds or gold, a reality that would be confirmed not by fantasy, but by the precise spectrographs of our space telescopes. If you've ever witnessed the iconic scene from Star Wars with the dual sunset on Tatooine, you have a sense of how captivating such a view would be. The most incredible part is that these worlds are not fictional. Planets orbiting 2 or even more stars have been officially added to astronomical catalogs. These are known as circumbinary systems when a planet orbits a pair of stars that are also orbiting each other, and Kepler 16b was one of the first to be confirmed. Its discovery was a landmark moment, proving that planets in multi-star systems can maintain stable orbits for billions of years, despite the intensely complex gravitational forces at play. However, binary systems are merely the starting point, as there are also triple-star systems, where the orbital mechanics become even more bewildering, sometimes resulting in nearly constant daylight, as one sun rises just as another is setting. On such planets, the temperature and light are governed by the planet's distance from each star and the unique light spectrum each one emits. If one star were a yellow dwarf and its companion a red dwarf, the planet would be bathed in shifting hues of light throughout its day. Imagine if one of those suns was a brilliant blue star. For part of the day, the entire world would be drenched in a dazzling blue-white glow, creating a landscape unlike anything you could imagine on Earth. Finding planets in these multi-star systems is an exceptionally difficult endeavor. The usual transit method is complicated by the fact that the star's light is constantly varying, and their own orbital dance can easily obscure the faint signal of a passing planet. In spite of these hurdles, observatories like the Kepler telescope have enabled us to identify dozens of these worlds, fundamentally proving that life in the universe could emerge and persist in far more exotic environments than we ever thought possible. If humanity ever seeks a new celestial home, you might find us considering a world with 2 or even 3 suns, where every sunset is a magnificent cosmic event. You should know that a star's death doesn't automatically spell doom for its planets. In some cases, these worlds can persist in orbit around a dead star, becoming cold and irradiated, but fundamentally intact. It's even possible for entirely new planets to coalesce from the debris left in the wake of a star's catastrophic demise. Among the most remarkable scenarios are planets discovered orbiting pulsars, which are the incredibly dense remnants of stars that have undergone a supernova explosion. Pulsars act like cosmic lighthouses, emitting powerful radio beams with a precision that is truly astonishing. It was this exact regularity that enabled the first-ever discovery of exoplanets in 1992, found orbiting the pulsar PSRB 1257+12. This find was a profound shock to the scientific community, as nobody had imagined that planets could either withstand a supernova or reform from its ejected matter. Worlds have also been found around white dwarfs, which are the hot but inert cores left behind by stars similar to our own sun. These planets might be resilient survivors that weathered their star's red giant phase, or they could be new creations formed from the surrounding gas and dust disks. A fascinating case is the object WD-1856+534b, a giant planet that circles its white dwarf in just 1.5 days. The mystery of how it got into such a close orbit remains unsolved, though it's possible its trajectory was altered after its star died. Planets orbiting neutron stars represent the most extreme examples, as they endure unimaginable levels of radiation and immense gravitational tidal forces. Life is theoretically impossible under these conditions, unless a world is shielded by an exceptionally dense atmosphere or a subsurface ocean. Yet these planets fascinate scientists because they prove that planetary bodies can endure in environments once considered utterly inhospitable. Detecting such systems is a major challenge since white dwarfs are faint, pulsars emit in specific ranges, and neutron stars are practically invisible to optical telescopes. Nevertheless, every single discovery of a planet around a stellar remnant is a significant event that broadens our perspective on where worlds can exist. The most stunning realization is that planets can outlive their parent stars. Even if they are left as lifeless, frozen spheres scarred by cosmic explosions, their continued existence demonstrates the universe's capacity to preserve worlds that you would have thought were fated to vanish along with their sun. Picture a world without a single continent, island, mountain, or desert. A planet defined by an unbroken ocean stretching to every horizon. Astronomers refer to these as ocean planets, and there's a growing belief that they might be a prevalent type of exoplanet throughout the cosmos. While water covers about 70% of Earth's surface, on an ocean planet, the liquid could blanket 100% of the globe and reach depths of hundreds or even thousands of kilometers. On these worlds, water would constitute a massive part of their total structure, creating not just surface oceans but also deep, high-pressure layers of ice. This includes exotic forms like Ice 7 and Ice 10, which can only form under extreme compression. A prime candidate for such a world is Kepler 22b, which is located in its star's habitable zone and, based on our calculations, may be entirely submerged. Another potential example, GJ1214b, is a super-Earth whose measured density strongly implies it has a substantial water composition. Life on such a planet would likely develop along a very different path than it did on Earth. The absence of land means there would be no familiar mineral or soil cycles, forcing ecosystems to rely completely on oceanic biology. You could imagine immense fields of plankton, colossal algae, and deep-sea organisms adapted to pressures tens of thousands of times greater than our own. While the climate on an ocean planet might be more stable due to water's excellent heat distribution, the lack of dry land could hinder the rise of a technological civilization by limiting access to metals and solid ground for construction. The direct detection of an ocean planet is quite difficult, so astronomers must infer their presence by calculating a planet's density from its radius and mass. When the density is too low for a rocky world but too high for a gas giant, it's a strong indicator that you are observing a water-rich planet. These worlds are of particular interest in the hunt for life because water acts as a universal solvent, a critical ingredient for biochemistry. It's quite possible that on one of these ocean planets, we will make our first discovery of alien life. Even if it is just simple organisms adrift in an endless sea under a distant sun. In stark contrast to ocean planets where liquid water flows freely, snowball planets are worlds imprisoned in a thick shell of ice. On these planets, a global winter is eternal. The entire surface is entombed in ice that can be hundreds of meters or even kilometers thick, and the temperature never rises above the freezing point of water. You can find similar examples right in our own solar system, such as Jupiter's moon Europa and Saturn's moon Enceladus. Although their surfaces appear to be frozen wastelands, beneath the ice of these worlds lie vast oceans of liquid water, kept warm either by the planet's internal heat or by tidal heating from the gravitational pull of their parent giants. Snowball exoplanets can come into being through two different pathways. They might form in a distant orbit far from their star, where sunlight is too weak to melt the ice. Alternatively, a planet that started in the habitable zone could have its orbit shift into a colder region, or its star may have dimmed over time, causing its oceans to freeze solid. For any life existing in the subsurface oceans of these planets, the ice layer would serve as a crucial shield. The conditions below could remain stable for billions of years, protecting the liquid water from radiation and meteorite strikes. Life in these lightless depths would probably resemble the organisms found around Earth's hydrothermal vents, creatures like bacteria and worms that derive their energy from chemical reactions instead of sunlight. The atmosphere of a snowball planet, should it possess one, would likely be extremely thin or virtually non-existent. Because ice reflects the majority of incoming light through the albedo effect, it further cools a planet, locking it into a state of continuous winter. This process establishes a frozen climate system where the star's heat is simply not enough to thaw even small patches of the surface. For astronomers like me, these worlds serve as the universe's colossal freezers, giving us a chance to investigate ice chemistry, the long-term stability of oceans beneath the surface, and the potential methods by which life might be preserved under the most brutal conditions. Should humanity ever journey to such planets, we might discover not only water, but also ancient, slow-evolving organisms that have been waiting for their frozen home to be found. Gravity is the fundamental force that anchors you to the surface of our home, Earth. You likely take it for granted. Every object falls with an identical acceleration, and your weight never changes. But try to envision a world where gravity is several times more powerful than Earth's. There, each step would be a monumental effort, and every movement would demand an incredible amount of strength. Such planets can indeed exist, provided they are considerably more massive than Earth while still possessing a solid surface. For instance, so-called super-Earths, which are planets several times our world's mass with a greater density and radius, can have a surface gravity of 20 to 30 meters per second squared, a value 2 to 3 times higher than our own. This gravitational increase means that a person weighing 70 kilograms would experience a weight equivalent to 140 to 210 kilograms. The physical repercussions for any beings on such worlds would be tremendous. Life forms would likely be short and stout, equipped with dense skeletons and formidable muscles to counteract the relentless gravitational pull. High gravity would inhibit the evolution of large land animals, and if birds could even achieve flight, they would need incredibly powerful chest muscles and compact wings. The atmosphere on these planets would also be denser, as the strong gravity would retain more gas, leading to slower water evaporation and perhaps a permanent cloud cover, where rain would fall in larger, heavier drops, and sound would travel faster and with greater clarity. Of course, the opposite scenario also exists: planets with very low gravity. These worlds might be smaller than Mars and possess a gravitational force that is barely perceptible. On a planet like this, you could leap tens of meters into the air, moving as if you were nearly flying. This freedom, however, would come with a significant drawback, as the weak gravity would be incapable of holding on to gases, resulting in an atmosphere that is either exceedingly thin or completely absent. Astronomers identify potential candidates for planets with extreme gravity by carefully analyzing their mass and radius. A prime example is Kepler 10c, a super-Earth with a mass 17 times that of our planet, which would exert a monstrous gravitational force at its surface. If oceans exist there, they would be subjected to pressures found only in the deepest parts of Earth's seas, like the Mariana Trench. For future space exploration, such worlds would present an immense challenge. Escaping the gravitational pull of such a planet would require a tremendous expenditure of energy, making any attempts at colonization extraordinarily difficult. Nevertheless, they could represent stable and enduring habitats for life, especially if they are located within their star's habitable zone. Here on Earth, the shifting of the seasons is governed by the tilt of our planet's axis combined with its orbit around the Sun. Spring, summer, autumn, and winter follow one another in a reliable cycle, and even the most extreme winters or sweltering summers eventually yield to the next season. Yet, across the universe, there are planets where this familiar pattern is completely shattered, and seasonal cycles transform into magnificent and sometimes hazardous phenomena. The most extreme seasons typically result from a planet having a very pronounced axial tilt. For example, if a world is tilted at 60 to 80 degrees relative to its orbit, one of its poles could be locked facing its star for months or even years, bathed in perpetual daylight, while the opposite pole is plunged into constant darkness. When the planet completes its revolution, the situation flips, and the seasons dramatically reverse. Another cause for extreme seasons is a highly elliptical orbit. If a planet's path brings it exceptionally close to its star at one point and then swings it far away at another, its summers would become unbearably hot, while its winters would be lethally cold. On some of these worlds, the temperature difference between seasons could span hundreds of degrees. There are even planets where seasons can persist for decades or centuries. Imagine a world where entire generations are born and live through a single winter, after which a slow warming period begins, allowing life to thrive. Such environments could lead to the evolution of a truly unique biology, featuring species capable of prolonged hibernation, seeds that can lie dormant for decades awaiting the perfect moment, and intelligent civilizations that must plan their existence centuries ahead to align with these vast climatic shifts. Interestingly, you can find similar, though less dramatic effects right here in our own solar system. On Mars, for example, its axial tilt and orbit result in seasons that last nearly twice as long as they do on Earth. On Pluto, with its elongated orbit and the dim light of the distant sun, a single winter can endure for decades, while its summer offers only a marginal increase in warmth. For exoplanets with such intense seasonal changes, the question of habitability becomes exceedingly complex. Life would either need to be incredibly adaptable or have the ability to go dormant during the harshest periods. Any civilizations that might arise would have to engineer solutions for survival, such as enormous domes, subterranean cities, and food storage systems designed to last for many decades. From my perspective as an astronomer, studying these worlds helps us appreciate just how diverse the conditions for life can be, and the incredible ways it can adapt to survive. Perhaps one day, we will discover a planet where winter has held its grip for the last 500 years, and its inhabitants are now witnessing the dawn of their first spring in centuries, heralding a new era for their world. You are accustomed to 24-hour days, a rhythm that seems entirely natural. But the cosmos is filled with worlds where a single day can stretch on for weeks, months, or even last longer than a complete orbit around a star, meaning a day can be longer than a year. This strange phenomenon is tied to the specifics of a planet's rotation and the gravitational tug-of-war it experiences with nearby objects, a process often known as tidal breaking. When a planet orbits too near its star, gravity gradually slows its spin until one hemisphere is permanently fixed facing the star, leaving the other in perpetual darkness. You can see this very effect with our moon, which always presents the same side to Earth. For planets, this phenomenon is referred to as tidal locking, creating a world of stark contrasts between eternal day and endless night. Occasionally, a planet's rotation is so slow that its day stretches for hundreds of Earth days. Venus in our own solar system is a perfect illustration. Its day is 243 Earth days long, while its year is a shorter 225 days. Compounding this, its rotation is opposite to most planets, resulting in an extreme climate where day and night last for months, yet its dense atmosphere maintains a nearly constant temperature. On exoplanets with similarly slow rotations, the climate can be incredibly strange. The side bathed in starlight can reach scorching temperatures, while the far side plunges to temperatures near absolute zero. Between these two extremes exists a narrow twilight zone where conditions could be comparatively temperate. Scientists theorize that this sliver of land is the most likely area where any potential life might be concentrated. If a planet isn't fully locked but simply rotates at a glacial pace, the shift from day to night transforms into a monumental event. Picture a sunrise that unfolds over several Earth days, or a sunset that extends for an entire week. Such a cycle would fundamentally redefine the rhythms of life, forcing plants to evolve ways to store energy for the long day and endure the protracted night, while any inhabitants would measure their lives in months instead of hours. For astronomers, these worlds are particularly fascinating because they offer insights into how rotation influences climate and atmospheric dynamics. A long day could lead to slow air circulation and stable weather, or conversely, it could generate violent storms fueled by the severe temperature differences between the light and dark sides. If we were ever to set foot on such a planet, each sunrise and sunset would feel like a grand cosmic performance, unhurried, majestic, and prolonged, as if time itself had chosen to linger. Drifting through the vast emptiness of interstellar space are special worlds known as rogue or orphan planets, unattached to any star. These planets roam freely through the galaxy, completely untethered from any system, and concealed within the cold, absolute blackness. Scientists theorize that these celestial bodies can be created in one of two ways. They might form within a star system like any other planet, and later be flung into deep space by gravitational disruptions. Or they could form independently in space, akin to small brown dwarfs. The surface of a rogue planet is typically incredibly cold, since its only source of warmth is residual heat from its formation, rather than starlight. However, if such a planet is sufficiently massive and possesses a thick atmosphere, it could retain this internal heat for an extended period. Some theories even propose that liquid water oceans could exist beneath the frozen surfaces of these worlds, kept fluid by geothermal activity deep within the planet's core. Discovering these planets is exceptionally challenging because they produce no light of their own, only faintly reflecting the illumination of distant stars. The main detection technique is gravitational microlensing, which occurs when a rogue planet's gravity magnifies the light from a faraway star as it passes in front of it. Current estimates suggest that the population of rogue planets in our galaxy could be as large as, or even greater than, the number of stars, implying that interstellar space is far from empty. If these calculations are correct, The void between stars may conceal countless solitary worlds, each with its own distinct history and potentially unique environments. For future exploration, these planets represent a compelling target. Should they harbor subsurface oceans, life could have evolved there over billions of years, entirely cut off from the rest of the cosmos, resulting in unique ecosystems that developed in total darkness without any influence from a star. Imagine a research expedition discovering such a world. Upon landing, the explorers would be greeted by an unending night, with a sky full of stars stretching from one horizon to the other. Yet, deep beneath the surface could lie a warm ocean, alive with bizarre, sightless organisms. These would surely be some of the most enigmatic and mysterious planets you could ever find in the universe. In our everyday experience, we witness a single sun tracing a predictable path across the sky. But try to envision a world where 2 or even 3 suns ascend over the horizon simultaneously, bathing the landscape in a symphony of multicolored light. Such planets are found in multi-star systems, and their skies can be truly breathtaking. The most famous pop culture depiction is Tatooine from Star Wars, with its iconic twin-sun sunsets. In reality, astronomers have already confirmed the existence of planets that orbit 2 stars, known as circumbinary planets. Within these systems, the gravitational pull of 2 suns results in intricate orbits, making the cycles of day and night completely different from what you experience on Earth. The light a planet receives is determined by its distance from each star and their individual brightness, which can paint the sky in extraordinary shades, from warm gold to cool blue. If one star in the system is red and the other is white, the sunsets could produce a stunning fusion of warm and cool tones, potentially creating a double rainbow effect on the horizon. The climate on these worlds with multiple suns can be exceedingly complex, as 2 or 3 heat sources generate elaborate temperature variations and unpredictable day-night cycles. This can lead to a planet becoming either a scorched desert or a world teetering on the very edge of habitability. Life in such an environment would demand incredible adaptability. Plants might evolve different pigments to harness light from stars of varying colors, while animals would need to cope with unstable lighting and frequent shifts in temperature. Astronomers have already identified several real-world candidates for such planets, like Kepler 16b, which orbits 2 stars at a safe distance, bringing what was once science fiction into the realm of possibility. Just picture yourself standing on the shore of an ocean on a world like that. Imagine looking out over a glistening body of water that mirrors 2 suns, just as a third one begins its ascent, casting unforeseen hues across the clouds. Each day in such a place would be unlike any other, with every sunset presenting a genuine cosmic spectacle. Within the vast catalog of worlds astronomers have found, a special distinction belongs to what are known as hot Jupiters and ultra-hot super-Earths, planets orbiting so tightly to their stars that their atmospheres or surfaces scorch at over 1,000 degrees Celsius. On these planets, oceans are in a constant state of boil. Solid rock turns to vapor, and even metals can liquefy and run like rivers. The planet KELT 9b stands as a record holder, featuring an atmosphere where temperatures surpass 4,000 Kelvin, making it hotter than the surface of many red dwarf stars. In this extreme environment, molecules are torn apart into individual atoms, and the atmosphere is composed of swirling clouds of evaporated metals, such as titanium and iron. Another fascinating case is 55 Cancri e, a super-Earth orbiting so near its star that its entire year is completed in just 18 hours, with temperatures on its sun-facing side hitting around 2,300 degrees Celsius. These scorching worlds frequently feature atmospheric winds that rage at thousands of kilometers per hour, transporting vaporized materials from the blistering day side over to the night side. This dynamic produces an incredible effect where one hemisphere is heated to a white-hot incandescence, while the opposite side, although several hundred degrees cooler, is still far too hot to support any life as you know it. The cause for these brutal conditions is straightforwardly their nearness to the parent star. Orbiting only a few million kilometers away, these planets are drenched in a colossal amount of energy and are typically tidally locked, meaning one hemisphere is trapped in perpetual daylight, while the other exists in eternal darkness. For astronomers, these extreme worlds are invaluable laboratories for understanding how planets shed their atmospheres and how matter itself boils away into space. Some have even been observed with comet-like tails of gas and dust streaming behind them. While they will probably remain among the most unreachable destinations for any future space missions, their visual grandeur is simply astounding. Picture a vista with a crimson sky, mountains glowing with intense heat, and rivers of liquid metal snaking toward a horizon dominated by a massive, blinding star. When you think about other planets, your mind likely pictures either familiar Earth-like terrains or extreme environments featuring oceans of lava and perpetual night under multiple suns. Yet, modern astronomy continues to unveil discoveries that fundamentally challenge your assumptions about what a planet can be. A striking illustration is the planet HD 189733b, where observations suggest it actually rains glass, not as drops, but as sharp fragments propelled sideways by furious winds at speeds reaching 7 kilometers per second. A phenomenon enabled by silicate particles crystallizing in its superheated atmosphere. Consider the exoplanet GJ1214b, which is shrouded in an atmosphere so dense that starlight can hardly pierce through to its surface. Researchers theorize that this could be a water world, boasting oceans 1,000 kilometers deep where water takes on exotic states, like hot ice, that stays solid despite extreme temperatures due to immense pressures. Then you have the possibility of diamond planets, such as 55 Cancri E, where the colossal internal pressure might have compressed carbon into a crystalline diamond structure. Should that hypothesis prove true, a substantial fraction of the planet's mass would be pure diamond, giving it a value that, by Earth's economic standards, is simply beyond calculation. Just as staggering are worlds where the laws of physics operate in ways that feel completely foreign to us. Take Kepler 78b, which circles its star in a mere 8.5 hours, an orbit so tight it would fit entirely inside our own sun. According to our understanding, it is a world that shouldn't even be there, as tidal forces should have torn it apart long ago. It seems we are witnessing it in a fleeting moment before its inevitable demise. Other planets present themselves as chemical oddities, with atmospheres rich in helium, sodium, carbon monoxide, or molecular hydrogen in proportions never observed in our solar system. Such worlds compel scientists to broaden their models of planetary formation, demonstrating that nature permits a much wider variety of outcomes than we ever conceived. But maybe the most mind-bending worlds are the ones still waiting to be found, hiding out there with floating continents, liquid ammonia oceans, skies lit by black stars, or perhaps even engineered orbits hinting at the presence of technological civilizations. Each astronomical breakthrough serves as a reminder that the universe is not just bigger than you imagine, but profoundly stranger. The most incredible revelations might not be what we have already documented, but what is still hidden in the dark across billions of worlds, where physics explores infinite variations of what a planet can be. You might picture ice giants like Uranus and Neptune as frigid, desolate places, but they actually contain immense reservoirs of internal heat. Curiously, Uranus gives off less energy than it gets from the sun, whereas Neptune, despite being much farther out, radiates 2.5 times more heat than it receives. This discrepancy has prompted scientists to propose that dynamic internal processes, like gravitational contraction or the decay of radioactive materials, are at play. Beneath the top layers of methane ice and ammonia clouds, you can envision a vast ocean of superheated water and Ice 7, a unique form of ice that remains solid under the pressure of millions of atmospheres. Furthermore, volcanic activity is hardly exclusive to our planet. On Jupiter's moon Io, hundreds of volcanoes are constantly erupting, launching lava dozens of kilometers high. If you could transpose that level of activity to an exoplanet with a thicker crust and more powerful gravity, you could imagine a world in a state of perpetual volcanic upheaval. Whenever we imagine planets, our minds typically turn to the familiar worlds within our own solar system. You probably picture the scorched surface of Mercury, the thick clouds of Venus, our blue Earth, the red dust of Mars, the gas giants Jupiter and Saturn, and the remote ice giants Uranus and Neptune. Yet, orbiting distant stars, billions of other planets, known as exoplanets, exist far beyond our celestial neighborhood. The study of these worlds represents one of the most thrilling frontiers in modern astronomy. Only a few decades ago, the very notion of detecting a planet outside our solar system felt like something out of science fiction. The overwhelming brightness of stars, compared to the faintness of the planets orbiting them, made spotting one across such immense distances seem like an insurmountable challenge. Even the star closest to us, Proxima Centauri, is 4.2 light-years away, rendering any nearby planet a minuscule speck completely lost in its star's brilliance. But a groundbreaking event in 1995 permanently altered the trajectory of astronomy. The announcement by Swiss astronomers Michel Mayor and Didier Queloz of the first exoplanet circling a sun-like star was a pivotal moment. This world, designated 51 Pegasi b, was a giant similar to Jupiter, yet it orbited so near its star that its surface temperature soared to almost 1,000 degrees Celsius. This finding created a sensation and ushered in the modern era of searching for worlds beyond our own. Since that time, the techniques for identifying exoplanets have become far more sophisticated. The transit method, where astronomers observe the subtle dimming of a star's light as a planet crosses in front of it, has proven exceptionally successful, though it demands incredible precision to detect changes of just a fraction of a percent. Another powerful technique is measuring radial velocity, which identifies the slight wobble of a star caused by the gravitational tug of an orbiting planet, visible through shifts in the star's light spectrum. Eventually, space telescopes were developed specifically for the task of hunting for exoplanets. The Kepler telescope completely transformed the field by identifying thousands of potential candidates. Later, its successor, the Transiting Exoplanet Survey Satellite, or TESS, expanded this search to encompass nearly the entire sky. We now understand that planets are not an exception, but the standard. Almost every star is host to at least one, and many possess entire systems of diverse worlds. While Saturn is renowned for its magnificent rings, astronomers have found a contender that far surpasses it. An object named J1407b, which boasts a ring system potentially 200 times larger than Saturn's. If our own planet possessed such rings, they would utterly dominate our view of the sky, casting immense shadows that would lead to extended eclipses. This colossal structure is likely composed of dust, ice, and rock, and its sheer scale suggests the planet is quite young, as gravity and collisions would eventually cause this material to either dissipate or be absorbed. Consider Jupiter's Great Red Spot, a storm that has been raging for at least 350 years. Now, imagine exoplanets where similar hurricanes could persist for thousands of years without end. On worlds with dense atmospheres and rapid rotation, gigantic vortices can become permanent fixtures, perpetually fueled by the planet's internal heat and gravitational disruptions. Any life that could exist in such an environment would have to be perfectly adapted to constant, powerful winds and perpetual movement along air currents. A world might appear to be a total hellscape on its surface, but even there life could find a way. In subterranean caverns shielded from the blistering heat, it's conceivable that unique organisms could not only survive, but thrive. In the same way, even in the most frigid regions of the cosmos, warm environments might be concealed. Beneath kilometers of ice, as on Jupiter's moon, Europa, or Saturn's moon Enceladus, tidal forces can heat liquid oceans, creating potential havens for life shielded from cosmic radiation and severe temperature changes. Not every planetary orbit is stable and predictable. Some worlds are subject to gravitational influences from neighboring celestial bodies, causing them to wobble in their path and altering their distance from their star. This instability leads to extreme climatic cycles, swinging from deep ice ages to periods of scorching heat. While Earth's seasons are a gentle result of its axial tilt, the climate on these planets could undergo radical transformations over just a few decades, or even years. On Titan, one of Saturn's moons, you can find rivers and seas, but they are filled with liquid methane and ethane, not water. You can envision a planet where entire oceans are made of these hydrocarbons, providing a foundation for life based on a chemistry entirely different from our own. On such a world, you would witness downpours of methane instead of rain, and the landscape would be cast in an orange, hazy glow from the dense atmosphere. Some exoplanets, such as Kepler 7b, are incredibly reflective, bouncing back as much as 50% of the light from their star. This is due to the presence of massive clouds, which may be formed from droplets of metal or reflective crystals. If you were to stand on the surface of such a planet, the sky might shimmer with a silvery light, and the sunsets would be truly spectacular. The high albedo, or reflectivity, of these worlds is what makes them detectable to astronomers even across vast cosmic distances. Here on Earth, our magnetic field serves as a vital shield against dangerous cosmic radiation. Some exoplanets, however, possess magnetic fields that are tens or even hundreds of times more powerful. For perspective, Jupiter's magnetosphere is so immense that if you could see it from Earth, it would appear twice as large as the full moon in our night sky. Planets with such colossal magnetic fields could generate the most brilliant auroras imaginable, bright enough to be visible from space over enormous distances. While no concrete proof exists yet, Some astronomers have wondered if certain unusual observations could be attributed to technological activity. Should a planet be home to an advanced civilization, it might deliberately modify its atmosphere or adjust its orbit, creating detectable signatures that we could potentially identify. This is a core objective of the search for extraterrestrial intelligence, or SETI, to learn how to differentiate between natural astronomical phenomena and those that might be artificial in origin. What remains most incredible is the sheer variety of these exoplanets, ranging from gas giants orbiting so close to their stars that their atmospheres are boiling away, to rocky worlds that might hold oceans and atmospheres where life could emerge. When you look up at the night sky now, you can appreciate that each tiny point of light, every faraway star, could be the sun to entire systems of worlds we are just starting to discover. Our quest to find another Earth is truly just beginning. Discovering worlds beyond our solar system is a science of subtlety, relying on the faintest traces these planets leave behind. Because exoplanets are incredibly small and faint next to the brilliance of their parent stars, seeing them directly is a feat achieved only in rare circumstances. Consequently, astronomers have devised clever, indirect techniques to find them by observing their effects on a star's light and movement. One of the most fruitful techniques is known as the transit method, which has been responsible for the bulk of our discoveries, particularly by the Kepler telescope. Just imagine a distant planet crossing directly in front of its star, momentarily dimming its light by a minuscule amount. To detect this subtle, recurring dip in brightness requires incredibly sensitive instruments and long-term observation, often spanning several years. The main drawback is that this method is only effective when a planet's orbit is precisely aligned with your viewpoint. Otherwise, the passage goes entirely unnoticed. The radial velocity method is another powerful tool in our arsenal. As a planet orbits, its gravitational pull causes its host star to wobble in a small, repeating pattern. This subtle movement alters the star's light spectrum because of the Doppler effect. The light waves shift toward blue as the star moves closer to you, and toward red as it recedes. By precisely measuring these spectral shifts, we can deduce a planet's existence and even calculate its mass and orbital distance. While transit and radial velocity are the workhorses, other sophisticated methods exist, like astrometry, which tracks a star's tiny positional changes, and gravitational microlensing, which uses a planet's gravity to briefly magnify the light of a more distant star. Although direct imaging is exceedingly rare, using special coronagraphs to block a star's glare and reveal a nearby planet is a stunning achievement. More importantly, we can combine these techniques. For instance, using transit data for a planet's size and radial velocity for its mass lets us calculate its density, which helps you distinguish a rocky world from a gas giant. Our detection technologies are advancing annually, now allowing us to find planets the size of Earth. Looking ahead, we aim to analyze their atmospheres and perhaps even uncover direct evidence of life, all by interpreting the delicate variations in starlight. When I and other scientists first embarked on this search, the prevailing assumption was that other systems would mirror our own, with small rocky planets near the star and gas giants further out. However, the initial findings completely overturned these preconceived notions, revealing a universe far more creative than we had ever envisioned. Among the earliest and most startling revelations were the hot Jupiters. These are colossal gas giants that orbit their stars at incredibly close distances. A prime example is 51 Pegasi b, which circles its star in a mere 4 days. Surface temperatures can soar to between 1 and 2,000 degrees Celsius, causing their atmospheres to bubble away and sometimes form immense tails of escaping gas. For quite some time, the question of how these planets arrived in such extreme orbits remained a major puzzle for astronomers. We've also uncovered intriguing classes of planets like super-Earths, which are larger than our world but not quite as massive as gas giants. These can range from solid, rocky bodies with potential oceans to worlds enveloped in dense gaseous shrouds, with some being prime candidates for life if they reside in the habitable zone. Then there are the mini-Neptunes, a type of planet that falls between terrestrial worlds and ice giants, possibly featuring thick atmospheres over icy layers and even hidden oceans. What makes these worlds particularly compelling to you and me is that our own solar system contains nothing like them. Consider also the theoretical ocean worlds, entirely submerged in water thousands of kilometers deep, with a high-pressure ice layer forming over a warm core. Any life on such a planet would have evolved in a boundless aquatic realm. We've also found planets on erratic, elongated orbits, with climates that violently swing between frigid and blistering extremes. Beyond star systems, rogue planets wander through interstellar darkness, their only warmth coming from internal heat. Uncovering this sheer variety has revolutionized how we think about planetary formation, showing you that our solar system is just one of countless arrangements permitted by physics. In the quest for life beyond Earth, our primary focus is on planets within the habitable zone. This is the specific region around a star where conditions are right for liquid water to exist on a planet's surface. We prioritize water because here on Earth, it serves as the essential solvent for every life form we know. While we acknowledge that alien life could rely on different chemistry, starting with the familiar is our most logical approach. The boundaries of a habitable zone are determined by the star's luminosity. For a star like our Sun, this zone stretches from about the orbit of Venus to that of Mars. Simply residing in this zone isn't a guarantee of habitability, as numerous other factors like atmospheric makeup, a protective magnetic field, and geologic activity are critical. Different stars present different scenarios. Bright, hot stars possess broad habitable zones, but burn out too quickly for complex life to likely arise. Dim red dwarfs host very close-in zones where planets can become tidally locked, with one side in constant daylight and the other in perpetual night, though heat distribution could still allow for a temperate region. This has led us to adopt a more expansive concept of habitability, acknowledging that life could thrive in unconventional settings. For instance, you don't even need to be a planet in the traditional zone. Jupiter's moon Europa and Saturn's moon Enceladus both conceal vast liquid oceans under their frozen surfaces, kept warm not by a star, but by the gravitational squeezing of their parent planets. The existence of life could therefore extend beyond the classic habitable zone, as many factors are critical, including atmospheric composition, pressure, the presence of a magnetic field, and geological activity. Stars themselves differ, and each possesses its own unique habitable zone. For hotter, brighter stars, this region is located further away, but these stars have short lifespans, which might not be enough time for life to develop. In contrast, for dim red dwarfs, the habitable zone is situated much closer, which introduces a different challenge. Planets can become tidally locked to their stars, locked, constantly showing the same face to their star, resulting in a world that is scorching on one side and frozen solid on the other. Despite the extreme temperature differences on tidally locked planets, some hypotheses suggest that a substantial atmosphere or ocean could circulate heat, forming a livable ribbon of territory between the perpetually sunlit and dark hemispheres. This has led scientists to adopt the idea of a broader habitable zone, recognizing that life might thrive under less conventional circumstances. For instance, on Europa and Enceladus, moons orbiting Jupiter and Saturn, vast oceans hidden beneath icy crusts are kept liquid by powerful tidal forces, implying that even worlds outside the traditional habitable zone could potentially support life. To determine if an exoplanet is habitable, astronomers construct intricate models that account for a multitude of variables, from atmospheric chemistry and pressure to the greenhouse effect, planetary rotation, and even its axial tilt. You'll find that sometimes the slightest variation in one of these parameters can be the difference between a paradise and a completely inhospitable wasteland. This quest for planets within the habitable zone is more than just a search for a second Earth. It serves as a crucial method for comprehending just how special our own world truly is. Each new world we identify pushes the limits of what we consider possible, fueling our hope that somewhere in the vastness of the cosmos, another intelligent species might also be gazing up at their stars. While we aren't yet able to see the surface of a distant world directly, we have the capacity to analyze its atmosphere from tens or even hundreds of light years away. An atmosphere functions as a planet's unique fingerprint, holding encoded data about its chemical makeup, temperature, climate, and perhaps even the presence of life itself. The principal technique for examining the atmospheres of exoplanets is known as transit spectroscopy. As a planet crosses in front of its star from our perspective, a fraction of the starlight passes through its atmospheric layer. The gases present in this atmosphere absorb light at specific wavelengths, creating distinct gaps in the star's light spectrum. By studying these absorption lines, scientists can identify the substances present, such as water vapor, methane, carbon dioxide, ammonia, or even oxygen. The detection of water vapor, for example, could point to the existence of oceans or cloud systems, while the combination of methane and oxygen might signal biological activity, since a large amount of Earth's methane is generated by living organisms. These kinds of indicators are referred to as biosignatures, and the ongoing search for them represents one of the most vital frontiers in modern astronomy. Each discovery brings us closer to answering that profound question. Are we truly alone in the universe? There is another method for studying a planet's atmosphere, which involves observing it during a planetary eclipse when it moves behind its star. By comparing the star's light spectrum just before and after the planet vanishes, astronomers can isolate the planet's own thermal emissions. This data can then reveal its surface temperature and whether it possesses clouds or significant amounts of dust. It's clear, however, that planetary atmospheres exhibit enormous diversity, from hot Jupiters with air so hot it contains vaporized metals, to super-Earths, where a dense atmosphere creates a runaway greenhouse effect similar to Venus. Modern instruments like the James Webb Space Telescope have already started to perform detailed studies of exoplanetary atmospheres, and the initial findings have been nothing short of breathtaking. Scientists have found evidence of crystalline clouds, rain made of molten iron, and even hints of complex chemical reactions occurring deep within the layers of gas giants. Perhaps one day, hidden within the light spectrum of a distant world, we will finally find that subtle yet unmistakable signal, a sign that another fire of life is burning bright somewhere out there. Over the last few decades, we have catalogued thousands of exoplanets, many of which are so bizarre that if you saw them in a science fiction movie, you would dismiss them as pure fantasy. Yet they are all real and verified by observation. One of the most well-known is HD 189733b, a gas giant that completes an orbit around its star in a mere 22 Earth days. On this world, winds howl at speeds greater than 8,000 kilometers per hour, and its atmosphere is filled with silicate crystals, meaning it literally rains glass. Not straight down, but sideways on the gusts of its ferocious winds. Then there is Kepler 16b, a world that orbits not one, but two suns. If you could stand on its likely gaseous surface, you would witness a double sunset on the horizon, a scene straight out of Star Wars, which not only creates a spectacular visual, but also leads to an incredibly complex climate with unpredictable days and nights. Another remarkable object is WASP-12b, an exoplanet so dark it absorbs nearly all the light that strikes it. Its surface is so intensely hot that its star is actively siphoning material away from it, gradually tearing the planet apart over what scientists estimate will be the next few million years, until only its core is left behind. Consider Kepler 438b, a super-Earth that initially presents a striking resemblance to our own world. This planet resides within its star's habitable zone and possesses a substantial atmosphere. Yet a significant issue remains. Its sun unleashes frequent powerful solar flares capable of sterilizing its surface, reminding you that being Earth-like is no guarantee of habitability. Then you have the genuinely bizarre world of 55 Cancri e, a rocky planet orbiting so close to its star that its surface temperature reaches to 1,400 degrees Celsius. A large part of its mass is theorized to be carbon, which under such extreme conditions could manifest as graphite and even diamond, potentially forming entire continents of precious stone beneath its crust. Every one of these finds broadens our comprehension of what kinds of worlds are possible, revealing a cosmos far more varied and imaginative than we previously conceived. It's conceivable that among this menagerie of incredible planets, one has already given rise to intelligent life, and we are simply yet to identify it. Nowadays, hearing news about the discovery of another exoplanet can feel almost commonplace. Just a few decades back, however, the existence of any planets outside our solar system was merely a hypothesis, not a confirmed reality. Scientists theorized they had to exist, as stars are born from collapsing clouds of gas and dust, and the surrounding disks should naturally coalesce into planets. But there wasn't a single confirmed case until the 1990s. That all changed in 1992 with a sensational announcement from astronomers Alexander Volstjan and Dale Frail. They had discovered planets orbiting the pulsar PSRB 1257+12. A pulsar is a type of neutron star, the dense remnant of a supernova explosion, which emits beams of radio waves with incredible regularity. Astronomers can detect even the slightest deviations in these signals with immense precision, and it was through these timing variations that they deduced the pulsar had planetary companions. This discovery was shocking for two main reasons. First, nobody imagined planets could even form, let alone survive, in the monstrously high radiation environment of a pulsar. And second, these dark, irradiated, and desolate worlds were the very first confirmed exoplanets in history. The genuine turning point occurred in 1995, when Michel Mayor and Didier Queloz of the University of Geneva revealed their discovery of 51 Pegasi b, a gas giant orbiting a star similar to our Sun. This marked the first time a planet was found orbiting a main-sequence star and introduced the world to the first-ever hot Jupiter. The technique they employed, known as the radial velocity method, would go on to become a cornerstone of the search for exoplanets. The discovery of 51 Pegasi b ultimately earned its discoverers a Nobel Prize and ignited a global effort, inspiring dozens of astronomical teams to begin their own systematic hunts for new worlds, ushering in a completely new age of astronomy. From that point forward, in just a couple of decades, we progressed from knowing of 0 confirmed planets to cataloging thousands of discovered worlds, ranging from rocky super-Earths to peculiar gas giants. What I find most incredible is that many of these discoveries were achieved using ground-based and space telescopes capable of measuring fluctuations in starlight as small as 0.001%. Each new exoplanet is far more than just another number in a database. It's a compelling story about the universe's boundless diversity, and a reminder that our Earth is just one of innumerable worlds adrift in the vastness of space. Without dedicated space telescopes, our knowledge would be limited to just a tiny fraction of the exoplanets we know of today. It was these instruments that elevated the search for distant worlds into a rigorous, methodical, and statistically robust field of science. The trailblazer in this revolution was the Kepler Space Telescope, launched by the National Aeronautics and Space Administration, or NASA, in 2009. Its objective was straightforward in principle, but incredibly challenging in practice: to stare at a single patch of the sky, continuously monitoring for the faintest dimming of starlight caused when a planet passes in front of its star. Kepler simultaneously observed approximately 150,000 stars, with a sensitivity that could detect brightness changes of less than 0.1%. Over just a few years, it identified thousands of potential exoplanets, including a great number of super-Earths, mini-Neptunes, and planets situated within their star's habitable zone. Because of this mission, we gained our first real statistics, which suggest that roughly 1 out of every 2 stars may have a planet similar in size to Earth, or slightly larger. This finding implies that our galaxy alone could contain tens of billions of potentially life-sustaining worlds. However, the Kepler mission had its constraints. It only surveyed a very small segment of the sky, and after a failure of its stabilizing reaction wheels in 2013, the mission had to be reimagined. It was rebranded as K2 and continued its work by observing different areas of the sky, though with somewhat diminished precision. In 2018, the responsibility of planet hunting was passed to a successor, the Transiting Exoplanet Survey Satellite, or TESS. Its mission is to survey nearly the entire sky, concentrating on the brightest and closest stars to us, which are perfect for detailed follow-up observations by other telescopes, including the James Webb Space Telescope. TESS has already logged hundreds of confirmed exoplanet discoveries and thousands more candidates. Its findings are frequently prioritized for spectroscopic analysis, which allows us to probe the atmospheres and compositions of these distant worlds. Furthermore, TESS uncovers highly unusual systems, such as planets with orbital periods of only a few hours, or systems where multiple planets engage in intricate orbital ballets. Together, these 2 remarkable telescopes have demonstrated that planets are not an anomaly, but a fundamental rule of the universe. It is entirely possible that somewhere in the data from Kepler or TESS, a world exists where someone is gazing at their night sky, asking the very same questions you and I do. The launch of the James Webb Space Telescope at the close of 2021 signaled a monumental leap forward for the field of astronomy. This next-generation observatory was engineered not just to peer at distant galaxies and cosmic nurseries, but also to analyze exoplanets with a level of detail that was previously unimaginable. It represents a new chapter in our quest to understand these worlds, moving from simply finding them to truly characterizing them. The James Webb Space Telescope, or JWST, relies on infrared spectroscopy as its main instrument, giving it the power to probe the atmospheres of far-off planets, identify the signatures of specific molecules, and chart their temperature landscapes. As a planet transits or is eclipsed by its star, the JWST is able to deconstruct the starlight, enabling an extraordinarily precise analysis of the atmosphere's chemical makeup. Within its initial operational phase, the telescope successfully identified indications of water vapor, carbon dioxide, and hydrogen sulfide within the atmospheres of worlds beyond our solar system. This progress signifies that you and I are on the cusp of being able to systematically look for biosignatures, the specific molecular combinations of oxygen, ozone, and methane that we associate with living processes here on Earth. The James Webb Space Telescope is currently focused on the most intriguing candidates previously identified by the Kepler and TESS missions, producing the very first in-depth profiles of these distant planets. A compelling example is the atmosphere of WASP-39b, where the telescope uncovered a sophisticated chemical environment, complete with proof of photochemical processes that have never been witnessed beyond our own solar system. The future of the ongoing quest for signs of life is intrinsically linked to upcoming initiatives. The European Space Agency, known as ESA, is getting ready to launch Plato, a telescope designed to find planets similar to Earth orbiting stars like our Sun. Meanwhile, NASA is advancing the LUVOIR project, an enormous telescope engineered to capture direct images of exoplanets by using either a specialized coronagraph or a distinct free-flying shield called a starshade to obscure the blinding light of their stars. These future endeavors will enable us to perceive planets as minuscule specks of light, allowing for their direct study independent of transit events. A further significant concept is the continuous monitoring of planets throughout their full orbits, which could reveal seasonal variations or even subtle changes in surface coloration, potentially indicating vegetation or other life-related activities. Ultimately, these efforts suggest that within the next few decades, we could finally obtain an answer to one of humanity's most ancient inquiries. Are we the only ones in the cosmos? It's possible that this profound answer will manifest as a faint line on a spectrogram, captured by an instrument silently gliding through the frigid vacuum of space. As you sleep, every world you observe, from our own solar system to the most distant ones, originated from an immense spinning cloud of gas and dust, through a process scientists term accretion. This cosmic construction begins when a colossal molecular cloud collapses, giving birth to a star. Surrounding this nascent star, a flattened, rotating structure known as a protoplanetary disk takes shape, rich with gas, dust, frozen particles, and mineral flecks. Inside this disk, a gradual yet unyielding accumulation of particles begins, as they collide and fuse, growing from millimeters to centimeters, and eventually to meter-scale objects. As these bodies grow, gravity's influence becomes dominant, leading to the formation of planetesimals, bodies measuring tens of kilometers across. The collisions between these planetesimals intensify, and out of this chaotic dance, the initial embryos of planets slowly take form. Closer to the star, the inner parts of the disk are much warmer, creating the perfect conditions for rocky worlds such as Mercury, Venus, Earth, and Mars to coalesce. Further out, past a boundary known as the snow line, the temperatures are cold enough for ice to remain solid. This region becomes the birthplace of gas giants and icy planets, because the solid ice adds significant mass to the planetary cores, enabling them to attract and hold immense quantities of gas. This planetary formation process is not always orderly. Sometimes giant planets drift inward toward their star, violently flinging other worlds out of the system or completely obliterating them. This very scenario is believed to explain the existence of hot Jupiters, massive planets orbiting far too close to their stars to have originated there. Protoplanetary disks serve as the cosmic laboratories for planet creation, and advanced observatories like ALMA now grant us incredibly detailed views of them, revealing rings and clearings that strongly suggest new planets are taking shape. It's fascinating that some stars host a multitude of planets in stable, organized orbits, while others end up with very few or none at all. The exact causes for this disparity are still being investigated, but likely involve the initial mass of the disk, the star's own activity, the influence of nearby stars, or even a close encounter with another star system. For any planet that does form, many factors, such as atmospheric composition, pressure, a magnetic field, and geological activity, are critical to its ultimate nature. Just as stars themselves differ, each one possesses its own unique habitable zone. Around brilliant hot stars, this zone is located at a greater distance. Yet these stars burn through their fuel quickly, potentially leaving insufficient time for life to emerge. In contrast, for cooler, dimmer red dwarfs, the habitable zone is situated much nearer to the star. But this proximity introduces a different challenge. The planet can become tidally locked, with one hemisphere perpetually baked by the star's heat, while the other remains in a permanent, frigid night. This tidal locking results in an extreme temperature gradient, with a scorching hot side and a frozen dark side. Nevertheless, scientists theorize that a sufficiently thick atmosphere or a global ocean could circulate this heat, potentially creating a temperate ring where conditions might be suitable for life. This has led researchers to adopt the idea of a more broadly defined habitable zone, recognizing that life could thrive in circumstances very different from our own. Consider Europa and Enceladus, moons orbiting Jupiter and Saturn respectively, where vast oceans are kept liquid beneath thick ice shells, warmed not by the sun, but by the constant gravitational squeezing of their parent planets. This demonstrates that a world located well outside the conventional habitable zone could still harbor the necessary conditions for life to exist. To determine an exoplanet's potential for life, astronomers construct sophisticated models that incorporate atmospheric chemistry, surface pressure, greenhouse effects, spin rate, and even the tilt of its axis. A minor variation in any of these factors can mean the difference between a thriving paradise and a barren wasteland. Ultimately, searching for planets in the habitable zone isn't merely about finding a new Earth. It's about grasping the very uniqueness of our own world. Every new planet you and I discover pushes the limits of possibility and reinforces the hope that somewhere in the boundless universe, another being is also gazing at the stars. The exact reasons for this variety aren't fully understood, but probable influences include the mass of the parent disk, the star's own activity, the presence of other stars nearby, and even dramatic events like the close pass of a separate system. As we learn more about how planetary systems are born, we move closer to resolving a fundamental question. Just how common is a solar system like ours? It's possible we represent a rare fluke, a perfect storm of stability and conditions suitable for life. Or perhaps millions of similar systems exist, each with its own unique history. While our own solar system is defined by 8 planets traveling in fairly stable, nearly circular paths, some other star systems are in a state of complete dynamic chaos. In those places, planets can orbit so tightly that a year on one might last only a few Earth days, and their mutual gravitational tugs establish intricate orbital resonances. The TRAPPIST-1 system serves as one of the most remarkable illustrations of this, where 7 terrestrial planets circle a small red star in a resonant chain, meaning each planet's movement is directly tied to its neighbors. This celestial dance ensures that when one planet finishes a specific number of orbits, its neighbor completes a synchronized amount, which gives the system an unexpected stability, despite the close quarters of its worlds. Such arrangements provide a fantastic opportunity for scientists to investigate the masses and densities of these planets. When 2 planets are locked in resonance, their gravitational forces gently influence each other, producing slight variations in their transit times. By measuring these oscillations, we can determine the mass of each world, even without observing it directly. At times, multi-planet systems can display far more chaotic behavior. Consider the Kepler 36 system, where 2 planets are so close that their orbits bring them within just 1.9 million kilometers of each other, a distance roughly 5 times smaller than that between the Earth and the Moon. One of these worlds is a rocky super-Earth, while the other is a gaseous mini-Neptune, making the stark difference in their sizes and compositions especially remarkable, given how near they are. There are also colossal systems containing more planets than we have. For instance, the star HD 10180 is known to have at least 6 planets, with some models suggesting as many as 9 could be present, creating a more densely packed version of our own cosmic neighborhood. These discoveries are profoundly important because they reveal the incredible diversity possible in planetary systems, proving that no single standard model exists. The universe appears to utilize every conceivable arrangement of mass, distance, and orbital configuration. By continuing to study multi-planet systems, we might one day discern which are stable for billions of years and which are fated for catastrophic change. And perhaps we will even identify systems where multiple planets reside within the habitable zone, raising the possibility that life could emerge on several worlds around the same star. When you picture a planet, you almost invariably think of it circling a star, our sun providing warmth to Earth, or an alien star lighting up a distant world. Yet, space is also home to a different class of planets, those that have no star to call their own. Known as rogue planets or free-floating planets, these objects wander through total darkness, their only light coming from distant starlight, and the faint heat radiating from their own cores. Scientists speculate that our galaxy may contain more of these lonely worlds than it does stars. These planets might originate in conventional systems, only to be ejected later through powerful gravitational encounters. Imagine 2 giant planets passing so closely that one violently flings its smaller neighbor out into the void of interstellar space. Alternatively, a companion star making a close pass could disrupt planetary orbits, sentencing them to become eternal wanderers. Some rogue planets may have even formed in isolation, like miniature stars, but simply lacked the necessary mass to kickstart thermonuclear fusion, placing them in a category somewhere between gas giants and brown dwarfs. Life on such a planet seems impossible, since without a star, there would be no source of heat or light. However, scientists have developed some surprising theories. If a planet possesses a thick hydrogen atmosphere, it could effectively trap its internal heat for billions of years. Beneath a thick crust of ice, an ocean could be kept liquid by warmth from the radioactive decay of elements in its core or by tidal forces generated by a large moon. In theory, such an ocean could support life, even in an environment of perpetual darkness. Finding these objects is incredibly challenging, as they don't pass in front of stars to create transits, nor do they cause detectable wobbles in a star's orbit. The primary detection methods are gravitational microlensing, which occurs when a rogue planet's gravity bends the light of a more distant star as it passes by, and infrared telescopes that can spot their faint thermal signatures. Each discovery of a rogue planet serves as a powerful reminder that the cosmos is filled with unforeseen forms of existence. Worlds are not always bound to a sun. They can be cosmic outcasts, yet potentially harbor vast oceans, and, just maybe, the secrets of life evolving under the most extreme conditions imaginable. It seems the universe has a fondness for extremes, and planets are certainly no exception. Among the thousands of exoplanets now known, we have found icy worlds with temperatures approaching absolute zero, and blazing giants where metals boil and evaporate into the atmosphere. These extremes are crucial for helping scientists grasp the absolute limits within which planets can exist, and they reveal just how varied the architecture of worlds beyond our solar system can truly be. Let's begin with the super-cold planets. These bodies are either situated extremely far from their stars or, like rogue planets, have no star at all, causing their surface temperatures to fall to 200 Kelvin or even lower. A prime example is the planet OGLE 2016 BLG 1195LB, which was found using gravitational microlensing. While its mass is comparable to Earth's, it orbits a faint red dwarf at such a great distance that it is likely trapped in an eternal frozen night, where any ice would be as hard as rock, and any potential atmosphere would be completely frozen solid. Now, let's turn to the other end of the spectrum, ultra-hot planets, such as WASP-12b or KELT-9b. These worlds orbit so incredibly close to their parent stars that their atmospheric temperatures soar beyond 2,500 to 3,000 Kelvin. On these scorching planets, conditions are so extreme that even metals are vaporized, creating an atmosphere laced with gaseous iron and titanium, demonstrating a planetary environment that is almost beyond our ability to comprehend. The exoplanet, KELT-9b, circles a star that outshines most in our galaxy, subjecting it to such ferocious heat that its atmospheric molecules are ripped into their constituent atoms. In this environment, metals like iron and titanium vaporize, creating otherworldly clouds of metallic gas. You can also find what astronomers call ultra-hot super-Earths, which are terrestrial planets with surfaces that are actual oceans of molten rock. A prime example is 55 Cancri E, where the temperature soars to 2,000 Kelvin, likely creating a planet-wide magma ocean by day that forms a temporary crust at night, only for it to be melted away again by the following dawn. These planetary extremes offer scientists some truly unique research possibilities. Hot worlds become natural laboratories for investigating chemistry under conditions that mimic the interiors of stars, whereas cold planets provide models for understanding how water or an atmosphere can endure in a near-complete absence of warmth. Simultaneously, these discoveries serve as a stark reminder of just how comfortable our own world is by cosmic measures. We exist in a very specific temperature window where water can stay liquid, permitting life to flourish, a situation that, on the scale of the galaxy, appears to be a profound exception rather than a common occurrence. When you picture the movement of planets, your mind likely goes to a tidy arrangement like our own solar system, with all its worlds traveling in the same direction on almost perfectly circular paths. The wider universe, however, seldom adheres to such neat and predictable patterns. Astronomers have found exoplanets with drastically different trajectories, including highly stretched out, tilted, and even backward orbits, where a planet circles its star in the opposite direction of the star's own spin. Let's begin with the elongated orbits, which follow elliptical paths that bring a planet extremely close to its star at one point and swing it far out at another. Consider the exoplanet HD 80606b, which endures a stunning temperature fluctuation from about 500 to almost 1500 Kelvin as it makes its close pass by its parent star. This cycle of intense heating and rapid cooling generates unbelievable atmospheric storms, unleashing ferocious winds powerful enough to whip around the entire planet in a matter of hours. A different kind of orbital abnormality involves inclined paths, where planets in certain systems circle their star at angles of many degrees off the star's equatorial plane. These tilts are often the result of gravitational meddling from other planets or companion stars. The most puzzling orbital class is the retrograde orbit, in which a planet travels against the direction of its star's spin. While this might seem physically impossible, astronomers have confirmed the existence of such worlds, like WASP-17b, whose orbital directions were likely flipped by some kind of cataclysmic event. These peculiar orbits provide scientists with vital clues about the formation history of planetary systems, suggesting a past filled with gravitational skirmishes where some planets were flung into deep space, leaving the survivors on these bizarre paths. Analyzing these systems is also critical for our search for extraterrestrial life, as an unstable orbit could make conditions unpredictable. And yet, these worlds also demonstrate just how versatile and imaginative nature can be. It's not impossible that life could find a way to adapt to even the most unconventional celestial mechanics. If I mention the word planet, you probably envision something similar to Earth, with its composition of rock, water, and a surrounding atmosphere. Yet, space contains worlds with chemical makeups so strange they seem to have been pulled directly from the pages of science fiction. Among the most stunning examples are the so-called diamond planets, which could form in a carbon-rich region where immense pressures and temperatures in a planet's core would naturally lead to diamond creation. The exoplanet 55 Cancri E is a leading candidate, with a mantle that may be packed with diamond and graphite. Then you have metallic worlds. For instance, the exoplanet PSRJ 1719-1438b, which orbits a pulsar, is thought to be made primarily of crystalline carbon, potentially making it almost entirely diamond. In other systems, you might find a planet whose iron core constitutes nearly all of its mass. Just as surprising are the genuine snowball planets, where temperatures are so profoundly low that any atmosphere has frozen solid, blanketing the surface in crystal layers that could be kilometers deep. Even more speculative theories propose the existence of planets formed from pure quartz, or those abundant in rare minerals that are only found in minuscule quantities on Earth. Every one of these potential worlds serves to illustrate the breathtaking diversity of the cosmos, as a planet's chemical makeup is a direct result of the materials from which it was born. While our own solar system features just a handful of fundamental planetary types, the galaxy at large could be home to hundreds of different varieties. To astronomers, these aren't merely cosmic oddities, because a planet's chemical composition is the foundation for its climate, density, and geological processes. It's possible that someday we will discover a world where diamonds or gold fall like rain, a truth that would be verified not by imagination, but by the precise data from the spectrographs of our space telescopes. If you can recall the iconic sunset scene on Tatooine from Star Wars, you can appreciate what a captivating spectacle that would be. The most incredible part is that worlds like that are real. Planets orbiting two or more stars have moved from science fiction into the pages of official astronomical catalogs. When a planet revolves around two stars that are themselves locked in a mutual orbit, we refer to these as circumbinary systems. Kepler 16b stands as one of the earliest confirmed instances, and its discovery provided proof that worlds in such complex gravitational environments can maintain stable orbits for billions of years. This demonstrated that even amidst intricate gravitational dances, planetary stability is achievable. However, binary star arrangements are just the beginning, as triple star systems introduce an even greater level of orbital complexity. In some configurations, a planet might orbit a single star, while a more distant binary pair exerts additional gravitational pulls, causing constant disturbances. In other scenarios, a planet's orbit could be simultaneously influenced by all three stars, resulting in highly unusual cycles of light and temperature. Imagine how profoundly different life would be under these conditions compared to what you know on Earth. In a system with two suns, the familiar pattern of day and night could be dramatically altered, becoming either exceptionally short or incredibly long. You might experience times when both stars hang in the sky together, or witness one sun set only to have the other rise a few hours later, creating a state of near perpetual daylight. The climate on such planets hinges on their distance from each star and the specific types of light those stars emit. If one star is a yellow dwarf and its companion is a red dwarf, the world below would be bathed in shifting hues of light throughout its day. And if one of those suns were a hot blue star, a portion of the day would be illuminated by a brilliant, dazzling blue-white radiance. Pinpointing planets within multi-star systems is an exceptionally demanding task. The standard transit method becomes complicated because the combined light from the stars is constantly changing, and their own orbital movements can easily conceal the subtle signal of a planet passing in front of them. Even with these hurdles, facilities like the Kepler Space Telescope and advanced ground-based observatories have successfully confirmed the existence of dozens of these exotic worlds. These discoveries strongly suggest that life could emerge in cosmic settings far more alien than we typically envision. Should you ever contemplate a new home among the stars, it's possible one of the leading candidates could be a world with 2 or even 3 suns, where every single day concludes with a magnificent cosmic spectacle of multiple sunsets. When a star reaches the end of its life, it doesn't automatically signal the destruction of its planets. It's possible for worlds to persist in their orbits around a stellar corpse, cold, irradiated, but still intact. Furthermore, new planets can sometimes form from the very material ejected during a star's violent end, coalescing in the aftermath of cosmic catastrophe. Among the most compelling examples are the planets found orbiting pulsars, which are the ultra-dense remains of stars that have undergone a supernova explosion. Pulsars emit beams of powerful radio waves with incredible regularity, acting like celestial lighthouses. It was this precise timing that led to the very first discovery of exoplanets in history, found around the pulsar PSRB 1257+12 in 1992. The revelation was staggering, as few imagined that worlds could either survive a supernova or be newly forged from its remnants. You also find planets circling white dwarfs, which are the hot, dense cores of stars like our Sun that have ceased nuclear fusion. These planets might be hardy survivors that endured their star's red giant phase, or they could be entirely new worlds formed from a surrounding disk of gas and dust. A striking case is WD 1856+534b, a giant planet that completes an orbit around its white dwarf in just 1.5 days, though the reason for its dangerously close proximity remains a captivating puzzle. The most hostile environments of all are likely found around neutron stars, where any orbiting body would be subjected to unimaginable levels of radiation and crushing gravitational tides. While life as we know it would be theoretically impossible there, barring the protection of an extraordinarily thick atmosphere or a deep subsurface ocean, these worlds fascinate scientists. They offer powerful proof of the resilience of planets in conditions once believed to be completely fatal. Observing these kinds of systems is incredibly difficult, as white dwarfs are extremely faint. Pulsars emit signals in very narrow frequencies, and neutron stars are almost impossible to see in visible light. Because of this, every new discovery of a planet around a dead star is a minor sensation, expanding our understanding of where worlds can exist in the universe. Perhaps the most profound insight from all this is the sheer fact that planets can outlive their host stars. Even if they are rendered lifeless, frozen and scarred by cosmic explosions, their continued existence proves that the universe has a way of preserving worlds that you would have thought were doomed to disappear right alongside their sun. Picture a world entirely devoid of land. No continents, islands, mountains, or deserts. Just an unending ocean from one horizon to the next. You're imagining what astronomers call an ocean planet, a type of exoplanet they believe might be quite common throughout the cosmos. In stark contrast to Earth, where water covers roughly 70% of the surface, these worlds could be completely submerged, with liquid making up 100% of their area. The oceans on these planets wouldn't just be surface features. They could plunge to depths of hundreds, or even thousands of kilometers. Water could constitute a massive part of their total mass, creating not only vast liquid oceans, but also deep layers of compressed ice. Under the colossal pressures found in their interiors, you'd find exotic forms of water ice, like Ice 7 or Ice 10, which can only form under such extreme conditions. Astronomers have already identified potential candidates, like Kepler 22b, which orbits within its star's habitable zone, and calculations suggest could be completely covered in water. Another contender is the super-Earth, GJ 1214b, whose density points to a significant water composition. If life were to arise on such a world, it would develop in ways alien to you, as the absence of land would eliminate the mineral and soil cycles we know, forcing ecosystems to rely entirely on oceanic biology. You might find immense fields of plankton, colossal algae blooms, and bizarre deep-sea creatures perfectly adapted to pressures tens of thousands of times greater than on Earth. The climate on these water worlds could be remarkably stable, since the vast oceans would distribute heat very effectively across the globe. However, this very lack of land could pose a significant barrier to the rise of a technological civilization, making it incredibly difficult to access metals or construct lasting structures. Directly spotting an ocean planet is a challenge, so astronomers must infer their presence by analyzing a planet's density, calculated from its radius and mass. If a world's density is too low to be purely rock, but too high to be a gas giant, it's a strong indicator of a water-rich composition. These planets are a primary target in the hunt for life, because water acts as a universal solvent, a crucial ingredient for biochemistry. It's plausible that on one of these endless oceans, beneath a distant sun, we will discover the first evidence of alien life, even if it's just simple organisms drifting in the currents. In sharp contrast to ocean worlds where water flows freely, you have planets completely encased in a thick shell of ice, known as snowball planets. On these frozen worlds, winter is eternal, with the entire surface buried under hundreds of meters or even kilometers of ice, at temperatures perpetually below freezing. We have analogs right in our own solar system, such as Jupiter's moon Europa and Saturn's moon Enceladus, which are icy wastelands on the surface. Despite their frozen exteriors, these moons hide vast global oceans of liquid water beneath their icy crust, kept warm by the planet's internal heat or by tidal forces from their giant parent planets. Snowball exoplanets could come into being through two main pathways. One possibility is that they form very far from their star, where sunlight is too weak to ever melt the ice. Alternatively, a planet that began in a habitable zone could drift into a colder orbit, or its star could dim, causing its oceans to freeze over entirely. The thick ice shell on these worlds could act as a shield, protecting any hidden life in the subsurface oceans from radiation and meteor impacts, allowing for billions of years of stable conditions. Life in these lightless depths would likely be similar to organisms found near Earth's hydrothermal vents, creatures like bacteria and worms that derive their energy from chemical reactions instead of sunlight. Any atmosphere on a snowball planet would probably be thin, as the ice reflects the majority of starlight back into space, a phenomenon known as the albedo effect, which only serves to further cool the planet and lock it in its perpetual winter. This creates a frozen climate, where the star's energy is simply not enough to thaw even a small patch of the surface. For scientists, these worlds are like cosmic laboratories, offering a chance to study ice chemistry, the stability of subsurface oceans over eons, and the ways life might persist in the most extreme environments. Should humanity ever journey to one of these planets, you might discover not just water, but ancient, slowly evolving life forms that have been waiting in their frozen domain to be found. You are held to the surface of our world by the force of gravity, something you likely take for granted as everything falls with a predictable acceleration. Now, try to imagine a planet where gravity is several times more powerful, making every step a monumental struggle. Such worlds could exist if they are substantially more massive than Earth, while retaining a solid surface. These are known as super-Earths, and their surface gravity could reach 20 to 30 meters per second squared, which is 2 to 3 times greater than what you experience here. On such a planet, a person weighing 70 kilograms would constantly feel a crushing weight equivalent to 140 or even 210 kilograms. The physiological impact on any native inhabitants would be immense. You would expect life to be short and squat, with incredibly strong skeletons and powerful muscles, just to counteract the constant pull. High gravity would likely prevent the evolution of large land animals, and any flying creatures would need tiny wings and incredibly powerful chest muscles to get airborne. The atmosphere on these worlds would also be far denser, as the strong gravity would hold on to more gas, leading to slower water evaporation and perhaps a permanent blanket of clouds. Raindrops would be larger and fall with greater force, and sound would travel faster and with more clarity. But consider the reverse. A planet with very low gravity, perhaps smaller than Mars. On such a world you could leap tens of meters into the air, moving with an almost flight-like grace. The trade-off is that its weak gravitational pull would be unable to hold onto a substantial atmosphere, leaving it thin or nearly non-existent. By examining a planet's mass and radius, astronomers can pinpoint candidates with incredibly high gravity. A prime example is Kepler 10c, a super-Earth whose mass is 17 times greater than our own, resulting in what would be a crushing gravitational force at its surface. If you could find oceans on such a world, they would experience pressures comparable to the deepest parts of Earth's seas, like the Mariana Trench. This immense pull presents a major hurdle for future space exploration, as escaping its grasp would demand an astronomical amount of energy, rendering colonization nearly impossible. Yet, if situated within their star's habitable zone, these planets could offer remarkably stable and enduring environments for life to thrive. Here on Earth, you experience the familiar progression of seasons, governed by our planet's axial tilt and its journey around the Sun. This predictable cycle ensures that even the most extreme heat or cold eventually subsides. However, across the cosmos there exist worlds where this stable pattern is completely upended, transforming seasonal changes into magnificent and occasionally perilous events. Extreme seasons are most frequently caused by a severe axial tilt. For instance, on a planet angled at 60 to 80 degrees relative to its orbit, one pole might be bathed in continuous daylight for months or even years, while the other is plunged into unending darkness, a situation that reverses when the orbit is complete. Another factor that can create extreme seasonal shifts is a highly elliptical orbit. A planet following such a path would swing incredibly close to its star, resulting in scorching summers, before traveling to a distant point where winters become lethally frigid. On certain worlds, these temperature fluctuations could span hundreds of degrees. You can even find planets where a single season extends for decades or entire centuries. Picture a world where generations are born and live entirely within a global winter, only for a gradual thaw to begin, paving the way for life to prosper. These circumstances would likely foster a unique biology, with species that can hibernate for immense periods, and intelligent societies that base their long-term planning on climactic cycles lasting centuries. It's fascinating to note that comparable, though less extreme, effects exist right here in our solar system. On Mars, for example, its axial tilt and orbit result in seasons that last nearly twice as long as ours. The habitability of exoplanets with such dramatic seasons is an exceptionally complex question, as life would need to be either astonishingly resilient or capable of entering dormancy to survive. Any civilizations that arose there would need to engineer advanced solutions for enduring these epochs of intense heat or cold, such as constructing colossal domes or subterranean cities. From my perspective as an astronomer, investigating these worlds broadens our understanding of the sheer diversity of conditions that can support life and the incredible ways it can adapt. It's exciting to imagine that we might one day discover a planet where a 500-year winter is finally ending, and its inhabitants are witnessing the dawn of their first spring in centuries, heralding a new age. You are used to a 24-hour day, a rhythm that feels entirely normal. Yet, the universe contains worlds where a single day can stretch for weeks, months, or even exceed the length of its own year. A phenomenon arising from unique rotational characteristics and gravitational influences. A primary cause for these extended days is a process known as tidal braking. When a planet orbits too close to its star, gravity gradually decelerates its spin until one hemisphere is perpetually locked facing the star, while the other is cast in endless night. You can see this same principle with our moon, which constantly presents the same side to Earth. For a planet, we call this condition tidal locking. Venus serves as a perfect example in our own solar system. Its day lasts for 243 Earth days, which is actually longer than its year of 225 days, and its backward rotation contributes to its extreme climate. The climate on exoplanets with such slow rotational speeds can be truly bizarre. The hemisphere bathed in starlight can reach scorching temperatures, while the side in perpetual darkness can plummet to conditions approaching absolute zero. Scientists theorize that a slender band of twilight between these two extremes could offer comparatively moderate conditions, making it the most likely place for life to emerge. On a world that rotates very slowly without being completely locked, the shift from day to night would be a magnificent spectacle. You would witness a sunrise that unfolds over several Earth days, a cycle that would completely redefine the tempo of existence. These planets are captivating because they offer insights into how rotation influences climate and atmospheric dynamics. Prolonged days might lead to slow air circulation and stable weather, or they could trigger violent storms from the stark temperature contrasts. Should you ever have the chance to visit such a place, each sunrise and sunset would be a cosmic performance, a slow, majestic, and prolonged event, as though time itself were expanding. Wandering through the immense void of interstellar space are unique worlds known as rogue or orphan planets. These planets drift without a parent star, journeying freely across the galaxy, perpetually shrouded in profound cold and absolute darkness. Scientists propose two main pathways for the formation of these solitary worlds. The first theory suggests they begin their existence in a conventional manner within a star system, only to be violently cast out into interstellar space later on. This ejection is thought to be caused by powerful gravitational disturbances or other calamitous events within their home system. A second possibility is that they form directly in the vacuum of space, independent of any star, much like miniature brown dwarfs. The surface of these worlds is typically frigid, because without a star's warmth, their sole source of energy is the faint internal radiation left over from their creation. Yet, if such a planet possesses sufficient mass and a thick atmosphere, it could trap this internal heat for an immense duration, potentially fostering oceans of liquid water beneath its surface, warmed by geothermal forces. Locating these planets is an extraordinary challenge, since they produce no light of their own, only dimly reflecting the glow of faraway stars. The principal technique for their discovery is known as gravitational microlensing, which occurs when a rogue planet's path incidentally takes it in front of a distant star, causing its gravity to briefly magnify the star's light. According to current estimates, the population of these nomadic worlds in our galaxy could rival or even surpass the number of stars themselves. If these projections are accurate, then the vast expanse of interstellar space is not nearly as desolate as you might believe. It could be teeming with countless solitary planets, each carrying its own distinct history and potentially unique environmental conditions. These worlds are a prime target for future exploration, for if they do harbor subsurface oceans, life could have developed there for billions of years, completely cut off from the rest of the cosmos, resulting in ecosystems that evolved in total darkness. Just picture a research mission arriving at such a planet. Upon landing, the crew would be greeted by an eternal night, with a canopy of stars stretching from one horizon to the other. And deep below the frozen crust, they might find a warm ocean alive with bizarre, sightless organisms. Discovering a world like this would mean encountering one of the most enigmatic and profoundly mysterious celestial bodies in the universe. In your daily life, you are accustomed to seeing a single sun trace its predictable arc across the sky. But try to envision a planet where 2 or even 3 suns ascend over the horizon simultaneously, bathing the landscape in a symphony of colored light. Such worlds are a reality in multi-star systems, where the skies can present a truly breathtaking spectacle. The most iconic cultural touchstone for this is Tatooine from Star Wars, with its famous twin sunset. But astronomers have now confirmed the existence of planets orbiting 2 stars, which are known as circumbinary planets. Within these systems, the gravitational pull of multiple suns generates highly complex planetary orbits, leading to day and night cycles that bear no resemblance to our own. The sky's appearance would be extraordinary, painted in unusual palettes, if the stars have different colors and temperatures. Imagine a red star paired with a white one, creating sunsets that blend warm and cool tones into a double rainbow effect along the horizon. The climate on such worlds is subject to extreme complexity, as several heat sources produce intricate and often unpredictable temperature fluctuations. A planet might be scorched into a desert by an overabundance of energy, or it could precariously hover at the very edge of habitability. Any life under these conditions would need to be exceptionally resilient, with plants perhaps evolving distinct pigments to harness light from different stars, and animals adapting to shifting illumination and frequent temperature swings. Astronomers have already identified several real-world candidates for these planets, including Kepler 16b, which orbits a pair of stars at a stable distance, bringing science fiction scenarios to life. Imagine yourself standing on the shores of an ocean there, watching the water glitter with the reflection of 2 suns as a third slowly emerges, casting unexpected hues upon the clouds. On a world like this, every day would be distinct, and each sunset would be a magnificent cosmic performance. Among the diverse planets astronomers have catalogued, a special classification includes hot Jupiters and ultra-hot super-Earths. These are worlds situated so close to their host stars that their surface or atmospheric temperatures can climb to 1,000 degrees Celsius and beyond. On planets this extreme, oceans would instantly vaporize, rocks would turn to gas, and metals could flow as freely as water. A prime example of such an inferno is the planet KELT 9b, where the atmospheric temperature surpasses 4,000 Kelvin, making it hotter than many red dwarf stars. The intense heat on this world is enough to tear molecules apart into their constituent atoms, creating an atmosphere filled with swirling clouds of evaporated metals like titanium and iron that churn in its upper layers. Another fascinating case is 55 Cancri e, a super-Earth that orbits its star so tightly that its year lasts a mere 18 hours. On its day-facing side, temperatures soar to approximately 2,300 degrees Celsius. Scientists theorize that its surface might be dominated by vast oceans of molten lava, while its atmosphere is saturated with the vapor of incinerated rock. On hot planets, you'll often find atmospheric winds blowing at thousands of kilometers per hour, transporting vaporized materials from the blistering day side to the night side. This results in a truly striking phenomenon, where one hemisphere glows white-hot, while the other, although cooler by hundreds of degrees, is still far too scorching for any life as we know it. The cause of these harsh environments is straightforward: their sheer proximity to a parent star, sometimes orbiting just a few million kilometers away and absorbing immense radiation, often leads them to become tidally locked, with one face permanently seared and the other cast in perpetual darkness. From a scientific standpoint, these worlds provide invaluable laboratories for understanding how planets are stripped of their atmospheres and how their matter bleeds into space. In fact, some of these searing exoplanets have been observed with comet-like tails of gas and dust streaming behind them. While these destinations will likely remain among the most unreachable for any future exploration, their visual grandeur is undeniable. Just try to picture a world with a crimson sky, where mountains radiate a white heat and rivers of molten metal snake toward a horizon dominated by a colossal, blinding sun. When you think of other planets, your mind likely defaults to either Earth-like vistas or extreme scenarios featuring lava oceans, unending night, or multiple suns. Yet, modern astronomy consistently uncovers worlds that shatter our preconceived notions. A prime example is the planet HD 189733b, where observations suggest a rain of glass, not as droplets, but as sharp fragments propelled sideways by ferocious winds at speeds reaching 7 kilometers per second. Such an event is made possible by its atmosphere's unique chemistry, which is rich in silicate particles that crystallize in the superheated air. Another world, GJ1214b, is shrouded in an atmosphere so dense that it chokes out almost all starlight, leading scientists to theorize it could be a water world with oceans up to 1,000 kilometers deep. In such an environment, water could exist in bizarre states like hot ice, which maintains a solid form despite extreme temperatures due to immense pressure. Then there are the proposed diamond planets, such as 55 Cancri E, where intense internal pressure may have converted carbon into its crystalline form. If this is true, a vast portion of the planet could be pure diamond, giving it a value that is, by any earthly measure, simply astronomical. Just as remarkable are planets where the laws of physics operate in ways that seem completely foreign to us. Consider Kepler 78b, which completes an orbit around its star in a mere 8.5 hours, so close that its entire orbital path could fit within our Sun. Based on our current understanding, it's a world that shouldn't exist, as tidal forces should have torn it apart long ago. It appears we are witnessing this planet in a brief, fleeting period just before its ultimate destruction. Some planets present as chemical anomalies, possessing atmospheres composed of helium, sodium, carbon monoxide, or molecular hydrogen in proportions and combinations that have no parallel in our own solar system. These peculiar worlds compel scientists to revise and expand their models of planetary formation, demonstrating that the universe allows for a far greater variety of outcomes than we had ever previously imagined. Perhaps the most compelling worlds of all are those that still await discovery. Somewhere in the cosmos there could be planets with continents that float in the atmosphere, oceans of liquid ammonia, or skies lit by the glow of theoretical black stars. We might even find planets with artificially engineered orbits, hinting at the presence of advanced civilizations. Each new find serves as a powerful reminder that the universe is not just bigger than we realize, but profoundly stranger. And the greatest marvel may not be what we've already found, but what still lies hidden in the darkness. We usually picture ice giants like Uranus and Neptune as frigid, desolate places. But the reality is that they generate tremendous amounts of internal heat. Curiously, Uranus radiates less energy than it gets from the sun, whereas Neptune, despite being 1.5 times more distant, emits 2.5 times more heat than it absorbs. This discrepancy has led researchers to theorize that dynamic internal processes, like gravitational compression or radioactive decay, are at play. You can imagine that deep beneath their layers of methane ice and ammonia clouds lies an ocean of superheated water, and Ice 7, a unique phase of ice formed under millions of atmospheres of pressure. Volcanic activity isn't confined to Earth. On Jupiter's moon Io, for instance, hundreds of volcanoes erupt simultaneously, launching plumes of lava tens of kilometers high. If you were to scale up that level of activity on an exoplanet with a thicker crust and more powerful gravity, you could conceive of a world in a state of perpetual eruption. While its surface would be an uninhabitable inferno, it's possible that unique life forms could thrive in subterranean caverns, shielded from the relentless heat. Saturn is renowned for its rings, yet astronomers have identified a potential exoplanet, J1407b, that boasts a ring system that could be 200 times more massive. If our own planet had such rings, they would utterly command the sky, and their immense shadows would plunge the surface into long-lasting eclipses. These structures are likely composed of dust, ice, and rock, and their sheer scale may be a sign of the planet's youth, as gravitational forces and collisions would eventually either dissipate or consolidate this material over cosmic timescales. Jupiter's Great Red Spot is an atmospheric storm that has been churning for at least 350 years. But exoplanets may exist where similar hurricanes persist for thousands of years without end. On worlds with very dense atmospheres and rapid rotational speeds, gigantic vortices could become permanent features, fed by the planet's own internal energy and gravitational poles. Any life that might exist there would need to be perfectly adapted to constant, powerful winds and a nomadic existence carried on the atmospheric currents. Not all planetary orbits follow a stable, predictable path. The gravitational pull of neighboring celestial bodies can cause some planets to wobble, forcing them into eccentric trajectories that periodically carry them much closer to, and then farther from, their star. This orbital instability would create a world of chaotic and extreme seasons, with climates that swing violently between radically different states, a cycle completely alien to anything experienced here on Earth. This leads to severe climatic fluctuations, swinging from deep ice ages to periods of scorching heat. While the seasons on our world are governed by its axial tilt, the climate on such a planet could shift radically within just a few decades, or perhaps even years. On Titan, one of Saturn's moons, you can find rivers and seas not of water, but of liquid ethane and methane. Picture a world where vast oceans are composed of these hydrocarbons, potentially giving rise to life founded on an entirely different chemical basis than our own. Methane downpours would replace water rain, and the thick atmosphere would cast an orange, hazy light across the landscape. There are exoplanets, such as Kepler 7b, that reflect as much as 50% of their star's light, thanks to immense clouds that might be formed from metallic droplets or crystals. If you were to stand on such a world, the sky could have a silvery sheen, and the sunsets would be truly spectacular. It is the high albedo, or reflectivity of these planets, that allows astronomers to spot them from such incredible distances. While Earth's magnetic field shields us from cosmic rays, certain exoplanets possess fields that are tens or even hundreds of times more powerful. For example, Jupiter's magnetosphere is so colossal that if you could see it from Earth, it would appear twice as large as the full moon in our night sky. Worlds with these gigantic magnetic fields could generate the most brilliant auroras, visible from space across vast cosmic expanses. Although no proof exists, some astronomers theorize that particular unexplained observations could originate from technological sources. If a planet is home to an advanced civilization, it might modify its atmosphere or its orbit, creating detectable signatures. This is a primary objective for the search for extraterrestrial intelligence, or SETI, to tell the difference between natural events and possibly artificial ones. Even in the most frigid regions of the cosmos, warm worlds might be concealed beneath kilometers of ice, similar to Europa or Enceladus. On these moons, liquid oceans exist below a frozen crust, kept warm by tidal forces. Exoplanets with these features could be far more prevalent than we currently imagine, offering oceans that are perfect incubators for life, protected from cosmic radiation and wild temperature swings.